Okay, gaggle of people by the door. Time to grab your seats. I knew a 40-minute break wasn't long enough for this crowd. All right, we're remaining on schedule. Couple of quick announcements. The poster session is up. So if you didn't have a chance to look at that, it's right behind the registration desk. Those posters are there. During lunch, we have a formal, well, not formal, we have an official poster session with the authors after the last plenary session of the day. That's at very small print. I can't read it. It's like 4:40 this afternoon, but all the authors will be in the poster sessions in front of their posters this afternoon after the last plenary. So please do go see those. They'll be open today and tomorrow. We have noticed that there's a very nice courtyard outside and it's a beautiful Tucson day. Feel free to go out there, but feel free to bring your hotel room key to get back in. Otherwise, you have to walk all the way around the building. So we've run into that already. So, because they do lock that door. All right. Any other questions or challenges during the break that I hadn't heard about? We've heard rumors that live streaming is up. So hopefully there's people on YouTube watching us. Hello, YouTube. With that, I'm going to introduce Alan Stern. Alan Stern has deep ties to Tucson. I think a lot of you know him as the PI on the New Horizons mission that flew by Pluto a couple, gosh, is it 5 years ago now? 6. We're getting old, Alan. 6 years ago. He's here representing, is it Helicity or Helicity? Helicity Space, and Alan Stern, come on up.
Stephen, great conference, and thank you for the introduction. And that is a very bright light.
Yes, a very bright light.
All right, so I want to have a show of hands. How many people know about New Horizons? Ever heard about it before today? Right, first mission to the last planet. Right, how many people know that it was the fastest spacecraft ever launched? Right, it took 9.5 years to cross the solar system. To do that, we had to buy the biggest rocket that NASA would sell us, design the smallest spacecraft that we could imagine, and then top that biggest rocket, the most powerful version, by the way, of that biggest rocket, the Atlas V with 551, with a special purpose third stage. And the end result was such blinding speed that whereas Apollo missions took 3 days to get to the moon, we did it in 8 hours. That's 0.3 days. At that blinding speed that got us across the entirety of 3 billion miles to Pluto, it would take over 1 million years to reach Alpha Centauri. Clearly, we need better propulsion. And that's what I'm here to talk to you about. A startup company based in California named Helicity Space, which I'm privileged to be one of the advisors for. I'll tell you more about the company in just a couple of minutes, which has the explicit goal, it sounds like science fiction, but it's not, of developing a practical fusion drive in our time and to change the entire equation of how we do spaceflight, particularly around the solar system. So now we'll see if I can make the remote work. Maybe not. There we go. Okay, so the talk's in 3 parts. First, I'm going to talk a little bit about the company. Then I'm going to talk about the Helicity drive. And then I'm going to talk about an interstellar mission that we would like to fly, which does not go to another star, although its successors could. But it is, we think, a better way to skin the cat for the kind of, quote, near space interstellar missions that NASA is looking at. And I have to do all that in the next 12 or 13 minutes. Okay, so as I said, Helicity is developing a game-changing fusion drive, and it really is. It's people use that term game-changing a lot. This time we really mean it. Yeah. Okay. So this is a very high-power device, and yet it's compact. Now, when I say compact, it's still tens of tons, but it's not the scale of the pyramids or a nuclear power plant. This is something that can be launched by existing launchers. It's clean because it's fusion. There's no radioactive fuels that are required. It's scalable in that we have, and you will see, a variety of versions of this that can take us to very large payloads, even human class missions around the solar system. It's agile because it is continuously thrusting. You're able to abort a mission at any point. It's not like a ballistic trajectory like New Horizons, where once we got it going, there was no way to ever turn it around and bring it back. And it's reusable in the sense that the fusion drive allows us to send spacecraft out across the solar system, bring them in the drive back, fuel it up, and go do it again, and then do it again, and do it again. The same way that Falcon 9 rockets now fly again and again and again. Okay, so this is a cartoon drawing of sort of a cutaway of what this is about. It's been developed over a series of many years in terms of the requisite base technology, some laboratory demonstrations, a lot of modeling. You can see some of the organizations that are involved, ranging from Caltech to the Commercial Spaceflight Federation, the Fusion Energy Association, and others. And if I can go to the next slide. Let me talk to you about the principals in the company. These four individuals, they're all here in the room today. Set Yu, Stefan Lintner, Marta Calvo, and Jeff Newman. And if they would stand up so you know who they are and you can ask questions later in the conference. They're the four of them from Helicity. That's the executive team. And then there's an advisory team as well, which I'm a part of. They're on the upper left. And another one of our advisors is in the room. Is Pete still over there? Pete Warden, General Pete Warden, former NASA Ames Center Director and planetary scientist, in addition to many other things in his career. So that's the company's advisory team. I'm having a hard time with this device here. Oh, I just keep going the wrong way. I know, but it's a very sticky device. Maybe the battery's getting low. Okay, so we intend to fly the first fusion drive and to fly it as soon as we can. Okay, that'd be great. Let's do that. So, and we have a plan for developing this in 4 stages. Each stage is a 2 to 3 year development effort. We are at stage 1 and are currently raising the money for that stage, and very successfully, I should say. In fact, we're going to close our first investment round here just in a matter of weeks. And we're going to go from roughly a $5 million demonstration project, scale it by about an order of magnitude for the second stage, higher TRL demonstrations. Then we're going to take it to be an independent system, not plugged in a wall, not deriving power off the grid, but just like a spacecraft operating in a laboratory, still in the ground. That's about twice the price of step 2. And then with a demonstration mission out in space, flying into interplanetary space, which we think is about a $400 million enterprise. Add it all up, it's a little over $500 million, completely change the equation of how we do missions around the solar system and change the course of the human expansion into the solar system in the 21st century. That's about a quarter the cost of a football stadium. It's amazing to think that we could change the course of spaceflight on just that. Next slide, please. Okay, so I've told you a little bit about the company. Let me tell you a little bit about Helicity Drive itself, the drive concept. And Set Yu, who can raise his hand from the executive team, is really the plasma physicist who is the brains behind this. He developed a lot of this when he was a professor at the University of Washington up in Seattle and demonstrated it in a lab there before the company was formed. Next slide, please. So in fact, the central picture right there, dead center in the upper middle, is in Set's lab, an actual Helicity Drive prototype firing successfully. And a variety of enabling discoveries have allowed this to become now a commercial concern. And the Helicity Drive is entirely based around a magnetic structure in a plasma that's basically a double helix, just like DNA, which combined with another technology that allows us to compress the plasma as the magnetic field is moving out through the plasma arc, gives us the ability to basically put an afterburner on an electric propulsion system and turn it into a fusion drive. Next slide. And here you see both in the on the right side, plasma actually moving through one of these devices, and then on the left with individual time steps, how this really works. And we intend to develop 3 different classes, possibly 4 classes of engines, small, medium, and large, just like your shirt sizes. But the way that these scale is not by making a bigger and bigger and bigger propulsion system. It's not like chemical propulsion where we started off with relatively small engines and we ended up with, say, Saturn V F1 class engines. This is a little smarter approach. It's scaled by having more fusion guns. So you're adding engines. In the small version, only a half a dozen, or perhaps 16, and then going up into 21, and then going up into the 30s. And this allows us to get higher and higher fusion gains and higher thrust efficiencies until it eventually becomes self-sustaining, because the amount of energy it takes to sustain the engines driving the propulsion system is less than what the fusion is actually generating. Most of that energy going away to heat or to neutrons, for example. Next slide. Okay, so there have been a variety of physics-based experiments and numerical simulations that have taken place. And all across the bottom of that view graph, you can see a series of bullets, 5 or so in each of the 3 columns, of technologies that have already been demonstrated to prove this concept. I'm not going to read all 15 of them to you, but it's impressive what this company has been able to do on very small amounts of money to get this going. And it's so impressive that our first investment round is now looking to exceed its targets by a considerable amount, which we're pretty happy about because we'd like to do this as fast as possible. Next slide. So we have an ongoing integrated proof of concept demonstration that will be our step 1. I actually want to start on the right where there's a scale model. You see the human in that CAD drawing next to the laboratory low TRL scale demonstrator. And then the 8 black boxes are the big batteries that discharge into the drive to power it for the tests that we will do. There are 4 milestones that we need to be able to demonstrate with this in order to go to the following step. And we think we can do all of this with the funding that we're now anticipating over the next 24 to 36 months. Next slide. Okay, so this is either an eye chart or maybe you can see it better than I can. But there's a lot of details here for all of you to be able to look at after the fact about these different drives as we progress from small, medium, large up to extra large, and then very, very much larger systems that will ultimately be powered not by deuterium, but by helium-3 when that becomes available. And what those allow us to do is to fly these interstellar missions, robotic precursors to what will, we hope, ultimately be human interstellar missions a century from now, with really impressive speeds that make New Horizons look like a horse and buggy by comparison. Next slide. Okay, so let's talk about plans for this interstellar mission. And next slide, please. Our proposed idea is to fly either a large or extra large class mission that can get us to distances like the Kuiper Belt, 30 to 100 astronomical units, not in a decade, but in 1 or 2 years. And if we fly the XL class system, that's not going to be first generation. We can do it in a matter of months. We can reach the heliosphere edge in about 3 years with the large class system. And ultimately, we can do that as well in months with the kind of systems that are on our drawing boards. And we can get all the way out to the inner Oort cloud, 1,000 astronomical units away. Remember, we're continuing to accelerate. So the speed's going up and up and up because it's a continuous drive. None of this, the current mode for flying around the solar system is you get a really big rocket, it develops all your speed, and unless you've got gravity assist, you're coasting from then on. But not in this system, like electric propulsion, but on steroids, we can get out to 1,000 AU in about the time that New Horizons got to 30 AU. And that is a game changer. Next slide. So let's compare it to other proposals to do interstellar robotic exploration of the very local interstellar medium. NASA is doing a spectacular study. The work is being led by the Johns Hopkins Applied Physics Lab, the same folks who built New Horizons. That's looking at a robotic spacecraft with very conventional New Horizons-like big launch vehicle, Jupiter gravity assist, maybe a solar gravity assist, an O-berth maneuver. And it's going to achieve speeds of about twice what New Horizons can do. A factor 2 is a big amount. But in the end, it'll get you out to the Kuiper Belt in 5 to 7 years. And it'll only allow you to have a fairly small spacecraft like New Horizons, something the size of a baby grand piano to do it. Now, there's another mission that JPL is looking at called the Solar Gravitational Lens mission. And it uses a light sail for propulsion and a deep pass into the solar gravity well. It can get us all the way out to 600 AU, where the sun acts as a gravity lens so that we can look back past the sun at exoplanets opposite the sun on the far side and image them at unprecedented resolution, tens of kilometers, so that you could see the lights of New York City on the Earth at that resolution. But that mission still takes 25 years to get out to that gravitational lens. By comparison, a Helicity-powered mission could fly out in a much shorter period of time and carry a 5-ton payload. So we can do these amazing things that we could never otherwise do. We could carry a Hubble Space Telescope class aperture out there and really do astrophysics. With orders of magnitude more power that's available to run the instruments and to communicate all that data back to Earth, and many other advantages. So we think this is kind of a no-brainer, other than the fact that we have to develop and prove this technology that we talked about. 5 minutes. Okay, so if we can have the next slide, and I'm almost finished. Scientific objectives for a mission like this are really mouthwatering. And the JPL and APL studies have borne out the same thing that we have said. This is a great mission for planetary science, particularly the Kuiper Belt. It is a great mission for heliophysics. That's another division in NASA's Science Mission Directorate for studying not just the interstellar medium, but also the termination shock and the heliopause, the shape of the heliosphere, the energetic neutral atom ribbon that was discovered by the IBEX mission, all of that in one mission with all the instrument goodies that you want, because this is not mass starved. And it's great for astrophysics, exoplanet studies, the things that you will do at the solar gravitational lens. So this is the kind of flagship mission that we hope will come out of the heliophysics decadal survey. Next slide. And we can fly it with either of two architectures. One would be the L class or large class drives that will be available by demonstration about a decade from now, according to our business plan. And those could fly on a Falcon Heavy. The system is big, but it's got plenty of margin, plenty of mass margin to be lofted by an existing launch vehicle, the Falcon Heavy. And that system can fly the 5 tons of spacecraft and payload that we were talking about, along with the propulsion system that weighs about 34 tons. The XL, which is the really fast ship, that's a little bit further down the road, is much heavier, but not so heavy that it can't be launched. In fact, the NASA Space Launch System is big enough to launch this vehicle. Imagine that, launch something that can take us all the way to the stars, that could take us to Alpha Centauri in about a century. That's a tractable length for a robotic spacecraft. Voyager, intended to go only to Jupiter, Saturn, is now nearing its 50th anniversary in flight. They weren't even trying to do it. With these propulsion systems that Helicity is developing and existing launch vehicles, we can do interstellar missions robotically, launched in the 21st century, arriving in the 22nd century, and that's not science fiction. Next slide. So this brings me to the conclusion of our talk. We're all about going faster and farther. And I hope that with this talk, I've given you just a taste of what Helicity Space is up to, and what our ambitions are, and the very bright future that we see for interplanetary and interstellar travel with the Helicity drive. Thank you.
Thank you, Alan. So our first question, if you can make fusion work, why not do that first in the lab for commercial power generation?
Yeah,
The
I think
billions
that's-
you'd make as a provider of carbon-free energy, you could then fund interplanetary/interstellar travel on the side.
Except, and this was actually one of the first questions I asked when Helicity, the company, approached me to join as an advisor, is, I've been watching fusion power development on the ground for ground-based power production purposes, and it's been impressive in some regards, but it's always another 20 years off, and it's been that way for 50 years. And as Seth very well explained to me, this is much easier than doing a fusion power plant. This is really just an afterburner on an electric propulsion system that uses fusion technologies to achieve that high thrust and therefore that acceleration without many of the complexities that you would have if you had to try to have a sustained tokamak or other ground-based fusion power system. What's the second question?
Thank you. Actually, I'm going to combine a few here. Could you tell us about the fuel or the pulsed power source?
Well, the fuel for this system is initially going to be deuterium based, but we hope to go to helium-3 for a number of reasons. But first, we have to have sufficient helium-3 supplies to be able to make that happen. As to the pulse power, I'm going to actually ask if Seth can stand up and speak to that himself. You'll have to project a little bit. We got a mic for you.
It's a pulsed magneto-inertial fusion concept. So on the ground, it's going to be energy stored, electrical energy stored in capacitor banks that will be discharged into very high currents inside the plasma. And then you time it with the magnetic fields, external magnetic fields, to be able to compress the plasma to fusion conditions in a very short pulse.
Thank you. And I believe we're out of time, but the final question I'll try to answer myself. How can we invest in Helicity Space? Please talk to one of the 4 co-founders over there, presumably.
Stephane, Stephane's our company CEO. Go see Stephane. He's got a term sheet and he's finishing the round. There may be a chance for you to still get in.
That's perfect. Thank you,
All right,
Alan.
thank you very much.
Thanks very much. Alan, that was great. You kept it on time. I appreciate it. Thank you. We're going to switch to a remote participant. One of the folks who would have been here for NIAC is actually one of the people who organizes the NIAC Symposium every year is Dr. Ron Turner. And Dr. Turner would have been here in Tucson if NIAC had not gone virtual. As it is, we've got him on Zoom. I checked a few minutes ago. He was online. Ron, are you there?
Can you hear me? I turned the camera and the audio on.
Okay, there we go. We can hear you and we can see you. So I'm going to shut up and give you the podium. Thanks.
All right. Well, as said, I really am sorry that I'm not there in person. The entire NIAC staff was very disappointed that we weren't able to execute a face-to-face meeting as we had hoped in Tucson. So, it's a significant disappointment for all of us. I am glad that I have this one opportunity, at least, to continue to speak about NIAC at this program. The NASA Innovative Advanced Concepts Program. I'm the senior science advisor, the title I created for myself to stay away from the programmatics as much as I can. But but more of the staff that runs the NIAC is listed in the chart across the bottom. Jason Derleth, our program exec, Eric Eberly, our program manager, myself. I'm a contractor, by the way, not a NASA person, not a NASA civil servant. Kathy Riley, another contractor who's our outreach coordinator, John Nelson, and Frank Spellman. So with that, the next slide, please. NIAC is a relatively small program, and we live inside what's called the Space Technology Mission Directorate, inside the early stage innovation portfolio for NIAC. And their purpose is to foster those breakthrough things that might eventually work their way up that chain of technology readiness. Next slide, in the interest of staying within my 12 minutes. Okay, so for those few of you, I think, out there who are not familiar with NIAC, because I say that because there's lots of fellows in attendance, there's lots of people who we've corresponded with over the decade that we've been around in its current incarnation. NIAC's job is to support innovative studies of visionary yet credible concepts, and we really take seriously that we're looking for those that can change the possible in aerospace. Next slide, please. So we're looking for those things that are exciting. We're looking at those things that are unexplored, yet credible and relevant. And the credible and relevant is sort of wrapped up in one of our most unique features as a NIAC program, as a NASA program overall, and that is you take your innovation and you put it in a mission context and show us that that your cool idea has a benefit, and it can be reasonably well shown that it actually works in a mission context. Okay, so we don't fund you to develop your special sauce. We fund you to show that your special sauce, should be funded is really one way of putting that. And you do that by putting it in a mission context. Of course, along the way, you have to do some of the work on your innovation to show the credibility and viability of your innovation. Next slide. We've got basically really two main phases. There's a third phase that I'll get to in a second, but the heart and soul of NIAC is their phase one. Phase one are, that's a 9-month study, which had been 125K for 9 months. It's now, this iteration, it's up to 175K for 9 months. We hope to push that up a little bit further, even as early as next year, perhaps 225K for the 9 months. But the purpose of the phase one is really to say, hey, I've got this really cool idea. I'm not really sure if it works. Let's see if it works. Okay, let's see if it might work. Okay, and you use that phase one to help establish the fundamental credibility of your idea. Some of the phase ones then advance to phase two. Phase two is a 2-year program. It had been about 500K. This year, we're going to up it to 600K. Again, we have plans, if the budget works out, to up that a little bit more in the future. But the call that's going to come out this year is going to be for 600K. Phase two, the 2 years, you're supposed to take your idea, look at those tall tent poles that you identified in phase one, and work them out a little bit further as to what their credibility might be and what their challenges might be. In addition, in phase two, you develop what would be considered a roadmap for development after phase two. So, when your phase two is complete, what are the next steps? All right. And for a select few of those NIAC studies, we recently instituted what we call phase three. We really try to emphasize to the fellows that this is not a 3-phase program where you start off addressing the simple stuff in phase one, get to the harder stuff in phase two, and then really save the really tough stuff for phase three. That's not the kind of development program we're after. It's much more of an iterative spiral development, if you will. Phase one is meant to be self-contained. When you get to the phase one, you have a credible final report. When you get to the phase two, you have another credible final report that increments on your phase one. Phase three are for those very few NIAC studies that have elicited enough interest in the community that there is an identified partner at the other end that says, if they can only solve these last couple of things, we actually are standing by ready to develop that idea. So to bid to phase 3, you really need to have that next level partner identified. They don't have to contribute. We're not requiring cost sharing. Cost sharing is good in phase 3, but they have to show an interest in what you're doing. And you have to be close enough that 1 or 2 key things done in a 2-year, $2 million study could reasonably be closed. And we funded 4 of those, as I'll mention a little bit later. Next. Overall, our program, as I say, we just hit the 10-year mark for the NASA Innovative Advanced Concepts program. Many of you probably remember that it was preceded by an external organization called the NASA Institute for Advanced Concepts. That one ran for about 9 years. And I was fortunate enough to have been senior science advisor for both the predecessor institute and the current program. But in its current incarnation, there was some concern when we went from the external to the internal program that NASA might get an undue advantage, or any number of things, because we're open to awards from anybody. And what we've learned, and it has not been, it's not been forced. There hasn't been a quota, but what we've learned is that between phase 1 and phase 2, we've actually evenly funded NASA, academia, and industry, because we're really just looking for the good ideas. We're not looking to, produce a congressional report that checks boxes. We're looking for those really good ideas. Now, phase 3, having only given 4 awards, the pie chart's going to be a little bit skewed by the small numbers. But speaking of numbers, and numbers that are not so small, in anticipation of our 10-year report, we did a review, and we've learned that we have received 3,787 proposals, leading to 175 awards. In phase 2, 258 proposals leading to 70 awards. And for phase 3, 51 proposals leading to 4 awards. So the numbers, are not insubstantial. It's been a wonderful community that has been contributing to NIAC's success. And it really is the fellows that cause our success. Next slide. I was asked to talk about how we impact IRG goals. And of course, the easy way to do that might have been to highlight some specific projects and say, look at what this project did, or look at what that project did. Lynn, thanks for distracting me with your text. NIAC funds topics throughout NASA. And the only way I could really do justice to this community is to say that, we have been funding space transportation projects such as nuclear, sails, plasma, beamed energy. We've been proposing human systems, life support and conditioning and habitats that might be useful downstream. We've been funding in situ resource utilization for lunar, asteroid, atmospheric mining. We've been funding robotics. We've been funding structures. NIAC is changing the perspective of what is possible. And I think that's our legacy here in regard to interstellar exploration. It is not imaginary that one could pursue an interstellar project. Okay, and I've only got a couple minutes left, so let me quickly go to a next couple more slides. Next slide. And the person driving, if you could just click all the way through until you see some dates show up, because this was originally built as a build. If you are interested in being a NIAC fellow, this is the pathway on how to get to a NIAC fellow. You start with your great idea, you write what we call a step A proposal, submit that step A. The step A goes to get some of the step A's. We got 300 step A's this year. A third of those were invited to step B. So it's a hard process right there. You submit your step B, you proceed then to technical review. This year we've got 5 technical panels looking at the 100+ step B proposals that we're looking at. Those get merged by an integration panel, which goes to source selection. Next year, the phase 1 call is going to again go out in early June. because of these steps that we go through, it'll be early February 2023 before we actually make the announcement of the awards. Next slide, please. So, what about this great new idea step? One of the things that we're proud of is it being a subject matter, a traditional subject matter aerospace expert is not an advantage to innovation, and we recognize that. Creativity is enhanced by diverse perspectives. And finally, the most interesting solutions are not the ones that are found in the answer section in the back of a book. I think there's another slide here, another step, 3 steps, go real fast. I think I'm preaching to the choir in this audience about the brainstorming, down selecting, and development. Okay, next slide. I'm hit my 12 minutes. So, and I do want to have time for questions. To propose for a NIAC phase 1, you go to our website to get the basic information. Oops, I'm dinging. And if you have questions, you can submit them to this website that's there. And I want to make everybody aware that one of the things we offer is more or less coaching on how to get your step A to be in scope and eligible for step B. Okay, it doesn't mean that we're going to give you necessarily a head start in the technical review step B, but at least we want to make sure that people understand what we're really asking for, and that if they have an idea, that their idea really fits within our scope. A lot of the people in the program office respond to questions about, am I in scope if I propose this? And I'm one of the ones that a lot of those questions go to, so I'm happy to talk to you about those. I think that might even be my last slide. So I rushed through this. I especially jumped through the section on, the specific steps, but I did that so that I would be sure to have as much of the 8 minutes as possible for questions.
Thank you, Ron. Well, we do have one question here. Do you have an estimate of the return on investment NIAC has produced over its last 10 years?
We always wish we could answer that question with, yes, here it is. It's, 25%, or here it is. It's whatever. But both in the Institute era and in the current era, the Innovative Advanced Concepts NASA run program, that's a real challenge. And it's a challenge for several reasons. One is that we specifically ask for you to propose those, kind of crazy ideas that aren't quite ready for prime time. And they take time to mature. And even, the time frame, even from Bob's time frame, it's hard to say, exactly how that worked out. We do have the interesting anecdote that one of the studies that Bob Casanova funded for the Antimatter was the inspiration for the Ingenuity helicopter that recently flew on Mars. And the PI for that program was the one to tell us that that was his inspiration for that Ingenuity thing. So when you're looking for, examples of success, that's an example. Pete Warden's in the audience, I understand, and Breakthrough Starshot is an example of a program that's funded. That was the Starshot part was built on a NIAC fellow idea. Now, we understand that Phil Lubin's concept had been pre-published in the Journal of British Interplanetary Society. So we can't say, that $100 million Starshot program is a return on NASA's investment, because a lot of factors factor in, a lot of influences and other things factor in. We've had some programs that have gone, that are going to flight, and we've had programs that have been demonstrated in the space station. So, we do have our successes. It's just we don't have an easy way to line those up in a numerical way, like maybe, this much money has led to this much money.
Okay, thank you. I don't have any other questions here, but we still have about 3 minutes left. So was there anything you would like to further elaborate on in your presentation?
Well, we had a wonderful symposium. We have our next year, we're going to have third time, hopefully will be, even though it was virtual. So that was a big mitigator. Third time we hope to be the charm. Next year, we are trying again to have our symposium in Tucson. So mark your calendar. It's going to be an easy date to remember. It's September 20 to 22, 2022. So, it's an easy date to remember. Don't even have to write it down almost. But we hope to see you there. Other than that, I'm glad to see the participation by the fellows in the workshop. Really wish I had been there myself.
Thank you, Ron.
Ron, thanks very much. We really appreciate it. Thank you. It's an amazing program. I used to work down the hall from Bob Casanova, and I would just go in and look at the things on his the proposals on his desk and go, those are really cool. So that's fun. That's fun. All right, we are remaining on schedule. I'm going to hand the microphone off to our glorious leader. Douglas Loss is the chair of the Interstellar Research Group, and he's going to talk about something that we've done at previous symposia, the working tracks. You're not here just to have fun. You're here to work. We're going to put you to work.
One of the things we try to do at the IRG Symposia is to give all of our attendees an opportunity to actually do some work. And we do that by holding what we call working tracks on different topics, where if you're interested in a specific topic, you can sign up to take part in that working track. And the working tracks do try to develop actual product. The working tracks this year are going to be led by Ken Roy, who is going to be discussing the book Dark Skies, and see if we can come up with a challenge, dispute, some sort of address response to it. And a working track run by Rob Hampson, which is going to talk about targeting habitable worlds. Now I'm going to ask each of them to come up and talk about their specific working track for a moment. Rob first, Ken second.
Hi, I'm Rob Hampson. I am on the programming committee for IRG this year, and I am the guy who actually came up with the topics for working tracks after some submissions and consideration of our talks. Now, you will notice that after each of our talks, we say we're going to have some questions only. They begin with an interrogative: who, what, where, when, how, and with a question mark inflection, and do not include statements, opinions, in my experience, or I have noticed that. Working tracks are your chance to actually follow up on that and have an opportunity to work and discuss. So we have two working tracks. We encourage everybody to participate who would like to pick one. And our comments in the program book say, please plan to attend both of the evening sessions. There will also be a read back on Monday morning. We do understand that there are some people who have scheduling conflicts that cannot attend both scheduling sessions. You are still welcome to participate. I'll say that right off the bat. So targeting a habitable world is going to have some of the discussions. Do we hold off everything until we find something that looks like Earth? We have a very strong risk that we head out to an Earth-like planet and find out that they've got odd proteins or nucleotides that would make life incompatible. So maybe we go for something that's close enough. And so this is a discussion where we talk about what the product would be from this is how risk tolerant are we? What are we going to look for? And why would we look for these things? Do we hollow out asteroids and live in the asteroids? Do we need a planetary surface with an open sky? Would you or would you not want domed cities in an atmosphere that doesn't quite work for total human habitation? And as I said, we can have these discussions, we can discuss them, and among ourselves, we can figure out what our risk tolerance is for the various alternatives. And so that's the goal that we have. Doug has also mentioned, if I can take just another moment, that in the past, we have had some definitive output from these projects and from these discussions. One of those was the book Stellaris, People of the Stars, which came out of the working track Homo Stellaris in 2016. And the book that you received in your packet, The Founder Effect, is another type of the output where we have taken the idea of, okay, so we do look for a habitable world. What does that look like? And we also try and look at some of the social factors, the political factors, and everything else that comes with it. So there are various types of output that may come of this, and we encourage you all to take part. And we will meet tonight after the banquet and start our discussions. Thank you.
Let's see, the working track I'm going to be heading up is concerned about a book by David Dudney. The title is Dark Skies. And the proposition he puts forth in that book is that expansion of humanity into the solar system is a negative thing. In fact, he puts forth the proposition that that may be an explanation to the Fermi paradox, that races that go into space manage to annihilate themselves. So we're going to look at his arguments and not necessarily take them apart, but the goal is to decide, does he have valid points that we need to begin to address? I've got some ideas, but again, a bunch of people brainstorming, I think, would be a lot more useful. So we're going to meet again tonight and tomorrow night to see, does he have any points that we need to seriously think about or not? So that's the topic, and hopefully we'll see some of you this evening.
Okay, one more thing, and then I'll hand it back to Stephen. This is news to Stephen. The Interstellar Research Group is hoping to expand our operations generally in a number of different directions, and to do so, we're going to need more people. So if you might be interested in taking a role in the Interstellar Research Group in various areas, which I'm not going to go into details right now, see Stephen or me sometime during the weekend, and we'll get your information and we'll be in touch.
Thanks, Doug. Appreciate it. Logistics for the working tracks, just because I didn't put that in up front, will be right here, except that wall will be closed during dinner. So after the banquet tonight, we'll have one in one half, one in the other half, and I forget which one we assigned, but it doesn't matter. You'll figure it out. But we'll be in these rooms. Please don't rearrange my furniture. Just move your chairs around, be friendly. We'll have flip charts up, we'll have a scribe, and that will run until y'all run out of steam, because those start, I believe, at 9 o'clock tonight and run until very late. So I hope you're able to take advantage of that. Those lead to very interesting discussions. So I hope you're going to be here. Okay, we are actually on schedule. So questions, comments, thoughts, arguments? Going too fast? Yeah, I know. I think I may have mentioned this morning. We were originally going to have 30-minute slots for speakers, and we just had too many good speakers. So we decided to compress everybody to 20 minutes and so talk fast. But it's actually worked out really well. We're about to break for lunch. Lunch is not in this building. That's on purpose because we want you to get outside and enjoy the beautiful Tucson weather. We're going to go outside of the Marriott and take a sharp right and it's the next building, so it's not very far. If you are walking and you encounter streetcar tracks under your feet, you went too far, turn around. It's a restaurant called Gentle Ben's. It's on the corner, the road directly outside the Marriott is Tyndall. It's at the corner of Tyndall and University. It's literally 50 yards. It's not far. We're going to have a couple of folks out there helping you to steer and get there and get back. Please don't get lost. The deal for lunch is if you have a regular badge, you're welcome to join us. If you have a yellow stripe on your badge, I'm sorry. Those are volunteers, and money, and lunch costs us money, so we're not able to feed the volunteers. We have a speaker set up there, so it's a buffet. We'll grab our food, sit down, socialize, but we'll then fire up the microphone. And Jim Bell, who's probably behind this bright light somewhere, but I can't see anybody. Jim Bell, who is the PI for Mastcam Z on Mars right now, but one of his other jobs is the Milo Institute. And so he's going to be talking to us about how Milo may work with interstellar work. So we'll have Jim Bell for lunch, and then back here at 1:30 sharp. So if you decide to wander away and do your own lunch, please be back here at 1:30. Questions, thoughts, comments? Dismissed to lunch. Oh, I'm sorry, I don't see. Where's a hand? Oh, it's up. Oh, I'm sorry, it's upstairs. Yeah, go through the restaurant. There's a staircase and an elevator if you need it. Just the staff knows we're coming. Just say you're with Interstellar, and they'll point you upstairs. They want to get you away from the normal people. They don't want you around. So, all right. Anything else? We are not planning to lock this room. I don't know how to lock this room. I can store stuff in the boardroom if you do it quickly, but I have to get over to the restaurant myself. Other questions? It's about 30, 35 minutes. So it depends on how quickly.
1, 2, 1, 2. This is mic check. Mic check.
Hi, are you talking to me? Did you want to check my mic?
Check, check, check. Blue handheld mic check. Oh, I think it's good. Down a little more. Yeah. Check, check. Podium mic check. Check, check, 1, 2. Mic check, 1, 2. All right, you shouldn't be yet. All right, check, check, 1, 2, 3, 4, 5, 6. Yep, I haven't turned these mics up yet for you. So how about now? Okay. Mic check, 1, 2, 1, 2, 3, 4, 5, 6. Yeah. So this knob right here, box 2, is the volume control just for that.
Okay, I think what's happening.
Very good.
Nobody's got it yet, so that's available. This area, so I think we're getting off. Read you off.
Yeah. All right. We'll start a clock when I hand the mic over. We're going to shift everything by 3-4 minutes to make sure that he gets full time. So yeah, we're about to get started. All right, there's a gaggle of people over by the door that need to find chairs. Come on. I'm actually impressed. We didn't lose that many people at lunch. So, you know, I thought hard about having lunch at a bar. And it's like, you know, are we going to get people back for the afternoon? But I think we had one table that stayed there, but other than that, people came back. So thank you. Hope you enjoyed lunch. Hope you enjoyed Jim Bell. He's an awesome speaker working on very cool stuff. About to switch gears. We're going to get a little more technical. Most people in this audience probably know Jeff Grayson. I've known Jeff for, again, longer than I want to admit. We probably met early 90s, mid 90s, 94. Not that we're counting. And we worked closely together for a long time on a project that ultimately was not successful, but we learned a lot, and we're still friends. Jeff has been a frequent speaker at the previous incarnations of this event, and really looking forward to his new work on wind pellet shear sailing. So Jeff, up to you. Glad you're here. Great. Okay, so we're at 8. All right. Shift everything by 5.
First slide, there we go. No, that's not the first slide. That's good. There's the first slide. So let me start by thanking my collaborators who are listed here. I'm going to move rather swiftly, so I will let you read their names. But they've been a tremendous help in getting this project reduced to a presentable state. Next slide. Yep, very good. Okay. I need to review some things that you already know, but it sets the context for where I'm going with this. Interstellar travel is fundamentally a problem because the energies involved are huge. If you want to send a no-kidding spacecraft, you know, something that includes luxuries like a power supply and a communication system and things like that, you're talking about payloads in the hundreds of kilograms. You know, we don't send flagship missions that are much smaller than that for good reason. If you leave some room for a propulsion system and call it, just to pick a round number, 1,000 kilograms, that's 1.8 times 10 to the 18th joules, 60 gigawatt years of kinetic energy embedded in that spacecraft, moving at 0.2% or 20% of the speed of light. Okay, big number. What's that mean? That if it was an antimatter rocket with the best efficiency we can imagine on paper you could get out of an antimatter rocket, you'd need to annihilate 120 kilograms of antihydrogen to get that velocity. You do not buy that at Radio Shack. If it was a fusion rocket with the best practical ISP that we have a hope of getting, 500,000 seconds, that would need 162,000 tons of fusion fuel. This is not a cheap mission. It's currently unavoidable with any of those strategies. Okay, this has been known for a long time. The obvious way around that is don't carry the power supply with you. Beam the energy in some fashion from the ground or from Earth orbit. Beamed momentum, you know, those systems are thought of as beamed energy, but they're really beamed momentum. You send a photon to the ship, it bounces off, it transfers its momentum to the ship. You send a particle, it bounces off, it transfers its momentum to the ship. That absolutely loosens the limits and it makes these things within the bounds of possibility. But when you start scaling up from grams to kilograms,
things start looking not so nice. The beam has to have enough range to keep the spacecraft in the beam while it's accelerating. And that means either you have to have a really high power beam so you can get a lot of acceleration done in a relatively short distance, or you have to hold the beam together over unphysically large distances. And I haven't tried costing out what the beam would look like for a 1,000 kilogram target, but I can tell you we can't afford it. It's a big beam. Okay, how do you get better than that? Well, the sail beam or pellet runway or pellet propulsion concepts are a way to evade those limits. You send guided macro particles, grains of sand, puffballs, something like that. Those are macroscopic objects. They don't spread out from thermal effects in vacuum, so they can, in principle, be made to go over quite a long range. That's a big help. It still doesn't get you down to the point where a 1,000 kilogram spacecraft starts looking affordable. And then the last step in this intellectual development is Jordan Kerr's idea, which, God, we miss him, which is the fusion pellet runway. Now, the advantage of that concept is you put down a trail of breadcrumbs of fusion fuel in front of the spacecraft. Okay, big advantage all of a sudden. The pellets don't have to go as fast as the spacecraft. Yay. But what that essentially is a seated Bussard ramjet. You run into the pellets, you convert their energy, and you use that to squirt out the reaction mass out the back. And just like a Bussard ramjet, you have to pay for the drag of running into the pellets. So when you start getting to large multiples of the kind of exhaust velocity you get out of a rocket, the mass of the pellet starts to skyrocket again. And it helps again, but not enough. We're still not there. Next slide. Okay. The holy grail for me for the last 5 years thinking about this has been, how do we get the energy from natural sources so we don't have to buy the beam? And last year's talk was a big step forward in that. The Q drive lets you take a big spacecraft going at a reasonably fast speed and turn it into a small spacecraft going even faster. That's a big help. But it does absolutely nothing to get you the kinetic energy in the first place. It just lets you concentrate that kinetic energy in your payload. You still have to get the kinetic energy from somewhere, and it's still a big freaking number. The problem is natural sources have limits on how fast we can get the energy out. 2 examples of that, both in the prior literature cited here. If you release little carbon puffballs, aerographite pellets close to the sun, they have such low density and can take such a high temperature, they pick up about 2% of the C leaving the sun from photon pressure. And tomorrow you're going to hear about some work from my friends at the University of Toronto that I've been helping with, not University of Toronto, I'm sorry, McGill, that talks about ways to get the solar wind energy harvested to get up to also about 2% of C. This is great. 2% of C is still not 6 or 7% of C. You still have a gap to close. Today is about how to close that gap. Oh, that does work. Okay, here's the big idea that you have to get your head around. I'll spend the rest of the talk talking about it. If the pellets are slower than the spacecraft that's running into them, but they're also moving in the interstellar medium, so they're faster than the interstellar medium. When you run into the pellets, there's a velocity difference that you're encountering between the wind that you run into and the pellets that you run into. Now, what does that let you do? Well, it looks different if you look at it in the ship frame or if you look at it in the rest frame. In the ship frame, it looks like I ran into this wind, I can extract power from the wind, and I can push on the pellets as my reaction mass. It's like having a roadway that you roll your wheels down, or as we call it for short, a pellet cog railway, where the gears engage the pellets as you go. In the rest frame, it looks different. In the rest frame, it looks like the ship ran into the pellet and it extracted the kinetic energy of the pellet and left the pellet at rest with respect to the interstellar medium. And the kinetic energy imbalance goes into the ship. This is hard to get your head around because it's a 3-body interaction. It's not a 2-body interaction. You have the wind, the pellet, and the spacecraft. Okay, so this is the basic principle. If you look at what the energetics are of running into a matter stream, in the limit where the wind or the velocity of object 1 is heavy compared to the velocity or mass of object 2, it follows the propeller equation. The power involved goes with the thrust or drag times the velocity. So the magic answer here is if you're running into two matter streams and you are running into them at different speeds, you want to extract energy from the fast one and you want to push on the slow one, because it takes less energy to push on the slow particles than you get out of running into the fast particles. So this is an example with numbers. I will not dwell on it because of time, but I just put nice, simple meters per second numbers in there so you can see for yourself afterwards how the numbers add up. You run into the things that going at 5 meters a second, you extract energy. You push on the thing that's going 3 meters a second. When you're done, both the energy and momentum have balanced and you've been left with a modest amount of thrust, which appears at first to come from nowhere. But it doesn't come from nowhere. It came out of removing the kinetic energy from the pellet stream. So when you start, the pellets are moving through the wind. And when you are done, the pellets are at rest with respect to the wind. That energy goes into the ship. Okay, there is if this seems confusing to you, don't feel bad. Lots of people have been confused by this over the years. There's a little physics bet that you can find on YouTube with the links shown down below, where a real physicist lost $10,000 betting that this couldn't work. But it does work, and it is hard to get your head around because you have to keep track of all 3 parcels of mass. So I will quickly try to play that. I don't know how to play it, but oh, there we go. So this is a vehicle in which once it's going downwind, the fast thing is the ground and the slow thing is the wind. It's going downwind. Initially, it's pushed by drag on the propeller. But if you watch the little telltale at the front of this vehicle, there's a little yaw string there at the front that's clearly pointing towards the nose because it's in a tailwind. And at some point here, it's going to start getting to the point where the telltale is pointing back at the pilot because it's going to be going downwind faster than the wind speed. There it is. It's exactly the same principle. There's 2 streams of mass passing the vehicle. One of them is the ground, one of them is the air. You can extract energy from that difference. That's actually also the same physics that racing hydrofoils can now use to sail downwind faster than the wind speed. Because in that case, the fast mass is the water and the slow mass is the wind speed. Okay, a little bit of equations here. This is the most simplified version of this. When you start factoring in efficiencies and finite masses, the equations get more complicated. But the analysis is easiest to do in the limiting case where the ship, you look at the rest frame. The ship's moving with the velocity of the spacecraft. It overtakes a pellet, has a certain kinetic energy. There's this mediated collision, this 3-body interaction that's going on between the ship, the pellet, and the wind. And when you're done, the pellet's at rest with respect to the wind, and the spacecraft has acquired velocity moving to your right on that diagram. And when you run the equations on that, the final velocity of the spacecraft is the velocity of the pellets. And assuming you start at the same velocity as the pellets, using whatever you push the pellets up to speed with to also get your initial velocity of the spacecraft, times the square root of the ratio of the mass of the total sum of the pellets that you picked up to the ship, plus 1, which is your starting velocity appearing in the equation again. This looks a little bit like the Q-drive equation because in both cases it's conservation of kinetic energy drawn up in a slightly more complicated form. However, note that if you don't get too greedy with this stage, in other words, if your desired final velocity is not too large a multiple of your initial velocity, that mass ratio gets to be not too scary a number. You know, if you want to triple or quadruple your speed, the pellet mass is on the order of 9 or 16 times, or 8 or 15 times in this case, the initial ship mass. Okay, that's not a very scary number. Next. Okay, to turn this kind of idea into hardware, there are three major things that you need. Well, four really. You need what we're calling the pellet dispenser, the thing that lays down the runway of the pellets, harvesting natural energies to do that. You need the windmill, just like the Q drive. You need the wind energy extraction system that you pass through the interstellar medium plasma and turn that into energy at the cost of drag. There were some options. You need the usual tricks, by say usual, that Jordan Kerr put a lot of skull sweat into, on how do you aim the pellets and how do you track the pellets and how do you steer the ship so that you can run over the pellet stream. One constraint we found about that is it does mean that there's a limit to how physically small you can make the pellets, because you need to be able to see them coming in time to steer the ship onto the center of the mass stream. But the solution to that turned out to be you make them very low density objects. You make them hollow, like a frozen soap bubble or an aerographite pellet or a piece of hydrogen snow, something very fluffy so that it has a nice big radar cross section when you run into it. And then you need what we're calling the pellet pusher, the thing on the spacecraft that takes the high velocity pellet coming in the spacecraft frame. You run into a pellet at high velocity and you leave it at even higher velocity. You've added energy to the pellet from the spacecraft's point of view. That turned out to be particularly challenging. There's not an awful lot of work being done on how you do ramjets at 3% of the speed of light that kick the pellets out at 5% of the speed of light. But we did find 2.5 promising avenues of approach for that. Cross-field accelerator and MHD type of accelerator. In that case, you have to heat up the incoming pellet hot enough to be a conductive plasma. That's not very hot. And then use J-cross-B forces to push it out the back. A linear macroparticle accelerator, basically a dust grain accelerator of electrostatic type. And we're still going back and forth on whether or not a thermal type of approach is possible. If it is, it involves a very, very hot plasma. But I include it on the list because there's some future work where that might turn out to be relevant. I've lost track of time. How are we doing? 5, okay. We're not gonna have a lot of time for questions, I'm sorry. I'll move through quickly a conceptual example of what this means for the mission. I'm looking at a 500 kilogram payload and just by arbitrarily, because obviously there's no engineering analysis here, but I have to do something to do the numbers. I've set the dry mass of each stage equal to its payload. You know, that's probably not of the wrong number of orders of magnitude, but it's by no means closer than I guess. There's a Q drive second stage that gets you from just over 5% of the speed of light up to 20% of the speed of light. We use 2% of C pellets, and we use that to push the whole stack up to about 5.5% of the speed of light. What does that get you? I'll cut to the bottom line. What that gets you is for your 1,000 kilograms of mass that ended up in Alpha Centauri orbit, because you can use the Q drive also as your brake at the other end. You needed a total launch mass of about 300,000 kilograms, or to put it another way, 3 Starship flights. Okay, that is by today's standards, that's a big mission. That's actually slightly larger than one Apollo Saturn V stack. But it's of the same number of zeros as an Apollo Saturn V stack. And you know, first you launch the pellet dispenser in the ship. The ship goes out to the outer solar system that starts building up velocity. The dispenser goes into the sun and gets ready to start dispensing pellets. A year later, you start laying down the runway. A year and a half after that, the ship leaves the heliopause towards Alpha Centauri and starts picking up the runway. A couple of years after that, you're up at 5% of C. You dump your first stage. Now you're on the Q drive. Takes about 4 years for the Q drive to get you up to 20% C. About 26 years after mission launch, you start braking. Takes about a year to brake. About 27 years after launch, you're in Alpha Centauri orbit. And about 4 years after that, you get your data back. This is kind of following the structure that Mark Millis was talking about for how we compare performance of missions. 30 years is short enough time that the principal investigator of the project can still be alive to collect the Nobel Prize. You know, nobody saying what technologies you haven't matured yet cost is a silly thing to do. But you can certainly look at what the absolute minimum it can cost is, which is the mass, the cost to launch all this stuff. Today, at today's launch prices, that's $600 million for launch cost. And I don't mean, that's not Starship, that's Falcon. And almost all this mass is the pellet mass. It's just inert mass that you're going to form into the pellets. It's not big, complicated spacecraft hardware. So there's no reason that can't go up on more than one launch. At a credible future scaling, it's not crazy to think that when we start doing things like mining lunar materials, we can get the cost of bulk mass down to $100 a kilogram. That would make the propellant cost for this mission on the order of $30 million for 1,000 kilograms, which is sufficiently cheap that thinking about scaling this up further to a human scale mission is not completely crazy, which is the first time I've been able to say that since I started looking at this field. And other options are very hard to cost also because they have their own technology gaps. So let me just say, this looks like it's got a different number of orders of magnitude in the cost number than any of the other alternatives I know about. Lots more to do. We need to take all of these elements to a much greater level of detail. This is all at the conceptual, how did the physics work level. The internal power flows of the vehicle can get very big, which is going to put a premium on either operating at a very high temperature so the radiator mass doesn't get crazy, or operating in a superconducting regime so the amount of waste heat that you have to manage is very small. It is interesting to consider marrying this idea and the fusion pellet runway. There's no reason why you have to run over inert mass. You could run over mass that's contributing its own energy to the problem, and that would be interesting to look at further. And I want to put a special thanks to the TVIW conference, which brought all the authors of this paper together to start this collaboration. So, you know, it's doing what it's supposed to do. And also to Matterbeam, who asked me the right question at the right time to help me get over a conceptual problem. And if there is any time left for questions, I will take them.
Thank you, Jeff. Yeah, we have time for a question. How far are the pellets spaced from each other?
Right now, the conceptual design maxes at 100 hertz of 0.01 seconds per running into them. In practice, that's thousands of kilometers apart from each other because you're moving really freaking fast. But a related question that we didn't get into is how long is the runway? And the answer to that is thousands of astronomical units. You launch pellets at 2% of the speed of light for years, and then you hoover up that runway as you're following it along. And with that being the one question, thank you, and I'll be around if there are more during the breaks.
Thank you, Jeff.
I am confident there will be more questions, and I'm confident that Jeff can answer them. So, very good. All right, thanks, Jeff. I appreciate it. Our next speaker is one of our NIAC fellows who could not make the trip because of what happened with NIAC. Lynn Rothschild with NASA, I believe NASA Ames, if I got that right. Her video looks like it's running already.
Yes.
We probably should back that up. She actually is going to. Yeah, can we restart her video? There we go. Lynn is actually appearing by video as
Please.
pre-recorded, but she will be doing the Q&A in real time after the video plays. So hit it.
Now, to go forth from planet Earth, humans take their needs with them. Human needs include transportation, Mars. So these structures are built with fungal mycelia. What are fungal mycelia, you may ask? Well, here is a mushroom. Everyone's familiar with mushrooms, but that's the fruiting body of a multicellular fungus. The main part of the body is composed of these thread-like structures called mycelia, mycelium singular, mycelia plural. Here's a micrograph I took of fungal mycelia. Now, it turns out that you can use these mycelia as a binding material, say binding wood chips, to make imitation particle board. Or you can use the mycelia themselves to make imitation leather. And so this has led to a field called mycotecture, something that's being explored on Earth because it's low mass, inexpensive. It's a great material, flame retardant, adaptable to building at site, and potentially self-healing. It's sustainable, compostable, and can be used for multiple things besides buildings themselves, tables, chairs, and so on. And many of these arguments for using mycotecture on planet Earth would also apply to using mycotecture off planet. So again, here is the vision that we have, thanks to Chris's beautiful rendition. And here's some of the things that we have already done in my lab. We have the fungal mycelium on the left growing on lunar regulus simulant, Martian regulus simulant, with just the addition of some nutrient solution. And you can see on the right, a stool built from using mycotecture that the students in my lab and the iGEM team made a few years ago. It only took about 2 weeks, including post-processing, for them to make the stool, which you can see created a very strong structure rated for the average Stanford student. So now that we're no longer limited by form factor, why not add bioprinting? Now, it turns out that biomaterials often rely on hierarchical structures. So when you look at a bird, even the feather of a bird, it's not a homogeneous substance. It's got all sorts of structures starting at the molecular level from the keratin monomers all the way through the next hierarchy, the nanostructure, where you have keratin filaments, then layered materials, and the macrostructure is the vein or the feather itself. So imagine using this approach where you bioprint bacteria, for example, that have been engineered to make the components of bone, and then you print bone and you end up with incredible structure. Maybe you're back to the future here. So our grand vision is that you use the sunlight to power photosynthesis, which then allows you to create all sorts of biological compounds that you then feed to a production organism, for example, a Bacillus subtilis that has been engineered to make nanocellulose, so an imitation of a cotton or wool or whatever, something that then could be used as the inputs for bioprinting, again, funded by the NIAC program. And you've now able to print whether it's an advanced composite or some kind of cool material that you use for clothing, or even a stake in space. Or medical devices or whatever. Here's another big idea for you, and that is that we will send digital information to make DNA. Now, up to very recently, if you wanted to make DNA, you had an organism that made it, and it had absolute physical continuity with the origin of life. But that's no longer true. Our students make up sequences in silico on their computers. They hit send to a DNA synthesis company. And the DNA synthesis company reads this information and takes it and makes the actual physical instantiation of the DNA. Now, my point is that it really doesn't matter whether this DNA synthesis company is across the hall from you or on a different planet or even a different solar system. The point is that we have now broken that physical link. Here's another idea for you. Biology does chemistry on the Earth, and it has throughout human history for us. Why not beyond Earth? And I think this picture pretty much sums it up for a Saturday talk. We will rely on nanotechnology just the way we do on the Earth, but much of nanotechnology involves having very large clean rooms and so on for synthesis. Not so if you're a cell. For example, the production of DNA involves incredibly precise nanotechnology. You have one amino acid wrong in a chain of proteins, you could end up with sickle cell anemia or who knows what. So the pressure to have absolute fidelity in DNA synthesis as well as protein synthesis is there. Now, we've harnessed that capability thanks to most of the work of Simon Vecchione, who started with me when he was a senior at Brown on an iGEM team in 2013 and is now a postdoc at NYU in New York. He has taken DNA and used that as a scaffold to create a wire. Now, it turns out DNA, the double helix, can be forced to have a mismatch. So two cytosines are across from each other rather than cytosine binding guanine. And when you have that cytosine-cytosine mismatch, you can incorporate an atom of silver with absolute precision. Turns out actually with the thymine-thymine mismatch, you can incorporate mercury. So using this big idea, you can not only make a wire 1 atom thickness, but you now have a way to extract metals. And this is something that we proposed and were funded by the NIAC program several years ago, and that is to take an integrated circuit, grind it, and use biological approaches to extract the metals and then reprint an integrated circuit. Now, we've talked about DNA and metal binding, but it turns out that, say, roughly 50% of the proteins in our body can also bind metals. I often tell people, if you want to know what metals we use as humans, go look at the back of a vitamin bottle. But it turns out they're not only the naturally occurring peptides, but they're also ones that have been designed to bind metals. A very common one in use in labs today is using a hist tag. So these are several histidine amino acids in a row, and they can then bind nickel, zinc, and cobalt. We've taken this capability, combined that with our mycotexture work by putting peptides on the surface of fungal mycelia that would bind copper, and then created a copper filter. We've published this, and we are now currently waiting on a patent. Here's another big idea. It's not just the electric eel that converts chemical energy into electrical energy. Every one of us does that every day. Presumably we're not eating to grow at our age, we're eating to do things like metabolize, and that includes making electricity. So in principle, that could be harnessed, but also why not create life 1.5, something my students have called the hell cell. So you take the capability of organisms that perhaps live at very high temperatures or low pH or whatever, and put those into other cells to allow them to have these capabilities. Or maybe life 2.0, life de novo. And there's a group of us under the rubric of an NSF research consortium network called the Build-A-Cell Network in the United States working on that. But there are also many international colleagues working on this whole idea of a bottom-up approach where the components of the cell are put together and with an attempt to make a living cell that can do all sorts of various things. Now, humans have needs, as I've mentioned many times, including for pharmaceuticals. And as NASA plans the Artemis missions to the moon and beyond, what happens when an astronaut gets sick? It's one thing when you have a short Apollo mission and you've carefully screened the astronauts, or they're on ISS and can come home. But what happens if you're moving on with no possibility for resupply? Well, astronauts currently bring in a very extensive list into space of medications. Now, the problem with bringing all these is you have an upmass issue, but even more important, you cannot predict the exact needs of the astronauts. You have the potential to run out of any given medication. But the real killer here is that some of them, particularly this new class of compounds called biologics, have a very limited shelf life of about 6 months. And so if you're talking about 2.5 year round trip to Mars, or certainly a much longer mission if you're going outside of our solar system, you simply have to make medications on site. So with this push towards long duration missions, you cannot do this carry everything approach. So we have proposed an astropharmacy, again, funded by the NIAC program with a wonderful international team of collaborators. And what we've proposed to do is, once again, to program Bacillus subtilis to make some of these pharmaceuticals and then have them produced in space, do simple purification steps, and have them ready for the astronauts. Now, it's time to test many of these ideas in space. So most of what I've showed you, we have proof of concepts with my lab or people affiliated with my lab. But many of these things have not been tested. And we were very fortunate a few years ago to be selected to have a secondary payload on the DLR Eucropus mission, Euglena Crops in Space. And what was particularly cool about this satellite is that it spun at 3 different speeds to mimic microgravity, lunar, and Martian gravity. And on this mission, we were able to test some of these very basic synthetic biology approaches, something we will talk about on another day. So in summary, we've talked about biology as a technology, and particularly synthetic biology and its use for exploration, particularly for in situ resource utilization, but in general to solve this upmass issue, including on-demand drugs, making habitats or other structures off planet, recycling metals, and so on. There are also scientific goals that we can use synthetic biology for, including making exploration platforms. We made a little biodegradable drone a few years ago, or astrobiology itself to understand the origin of life, the limits to life, the what if questions, and more recently, aeronautics, looking at green aviation, biofuels, and so on. But this may include novel materials and so on that are useful off planet. And now we see with in the wonderful insight that we do are now, well, we're now looking at aeronautics off planet. And so with that, I thank you very much for your attention. Ad Astra to the stars.
Thanks, Lynn. And with luck, you're on Zoom and able to join us real time, I hope.
I am. I'm here.
There we go. Great.
I'm sorry I'm not with you. I do apologize for not being with you. But I did think that the best thing would be pre-recorded, because even though I live above Silicon Valley, our internet connection is not the best. So I do apologize, but I'd be happy to take questions for however long I have.
Great. We've got a couple of minutes. So Dennis?
Okay, great. So here's a certainly a down-to-earth question. Does the binding of metals to fungal mycelia proteins in the human gut possibly account for leaky gut syndrome?
Oh, wow. I never thought of that. But actually, I just want to clarify that what we were doing was putting engineered peptides on the surface of fungal mycelia that we knew specifically would bind copper. It is true that there are some peptides on fungi that I believe can bind metals, and it's been suggested that some can be used naturally as a sop. So I don't know what effect that might have, or whether those proteins would normally be digested before you even got to your intestine or not. So it's an interesting question. I'll follow through on it, but I suspect you don't need to give up mushrooms.
Thank you. Here's another question. In de novo synthesis, do you plan to design cells from scratch or to remove the DNA from specific cells as quote unquote target organisms?
Again, fabulous question. I'm not doing a lot of that myself, but I went through this very quickly. What the question is describing is what's known as a top-down approach, which is something that, for example, the Venture Institute has worked on in Southern California, where you start to remove bits and pieces of cells, or you take out a whole nucleus and do a transplant. What many of the people in the community that I'm involved with that build a cell are doing a bottom-up approach, where they're making lipid vesicles and stuffing things into it. Lipid vesicles themselves are really easy to make abiotically. It's the old, shaking up a bottle of salad dressing with oil and vinegar, and you've got your little vesicles. And then it's a matter of putting things in. Some of it you can put in by having the DNA or whatever in the aqueous phase. Then you start to get a little bit more complicated, actually having the synthesis of proteins and so on, which you can do briefly, having those then inserted into cell membranes all the way to getting structural components in and having cells divide. But there's been a seminar series on Mondays where people around the world have given talks that it knocks my socks off every week. There is an amazing talk, and it makes me very confident that we're getting very close to having the different components of what a cell does being created artificially. Now, these may, in some cases, be very similar to what we already use and has evolved. Sometimes it's sort of a workaround, but again, the unbelievable work being done by my colleagues that will hit the front page of every paper at some point soon, I would imagine.
Wonderful. Thank you so much, Lynn.
Lynn, thanks very much. We appreciate it. That's
Thank
our time
you.
limit. And thanks for appearing live with us. And we want to see you in person in 2023. Thanks.
Oh, gosh, I want to be there. Thank you. Bye.
We're getting one. Wow, that's loud. We're getting one of our triple hitters up next. We have two of them on the agenda. Ken Roy led a seminar yesterday on terraforming. As you heard earlier, he's going to be leading one of the working tracks tonight on dark skies. But he's up now to talk about solar shields, or I'm not sure if I got the name right, but it's planetary protection from the sun. Ken?
Can everyone hear me okay? Any problems? We're good? Okay. I'm going to be talking about solar shields. The concept really is a geoengineering approach to solar radiation management in an effort to mitigate or even reverse global warming, which is a main driver of climate change. And how does this work? Just punch the button? There are lots of buttons here. Oh, okay, there. This thing's touchy. All right, the concept was first proposed by James Early, who usually makes it to these symposia, but he wasn't able to make it this time. He published an article in JBIS in 1989. And since then, a number of other people have published pretty much on the same concept, but they generally call it different things. Roger Angel is he here today? Okay. Anyway, he called it a cloud of small spacecraft. Other people have called it solar shields, planetary sunshades. A group I'm affiliated with calls it Dyson dots. And the overall idea is fairly simple. If you want to cool off the Earth, you just put an object between the sun and the Earth to intercept some of the sunlight that otherwise would hit the Earth. And because the overall energy input into the Earth is smaller, the temperature goes down. Well, let's go back here. Usually we talk about placing this at the Sun-Earth L1 point, but because really we're looking at solar sail type craft as our solar shield, we have to deal with radiation pressure, solar radiation pressure, and that forces the optimum point sunward of the classical L1 point. McInnes has looked at that pretty closely, and he's published a paper back in 2015 where he said, if you want to minimize the mass in order to affect a given radiation reduction, you have to go 2.44 million kilometers from Earth. The traditional L1 point is about 1.5 million kilometers from Earth. So this is pretty significantly sunward of the classical point, but that's the optimum point, it looks like at this point. Okay, how much solar shield do we need in order to cool the Earth? And here, let's look at the 1 degree C reduction. We need about 34 million square kilometers of solar shield. And how much mass is that going to be? Notice that there are two numbers here. The 21.2 megaton number is for dark sails, and that has an aerial mass, again, per McInnes, of about 6 grams per square meter. The large number, 127 megatons of solar shield, is for a highly reflective sail, and that's got an aerial mass of 36 or 37 grams per square meter. And to translate that into starships, which seems to be a unit of measure anymore, if you're going to use dark sails, you need 235,000 Starship launches for the dark sail. And if you want to use a highly reflective sail, you're looking at 1.4 million Starship launches. Because we probably will be somewhere between, the actual number might be between those two numbers. And if you want to, use a different temperature reduction, then you can see the other numbers. There's 1.5 C and 2 C. Okay, what does this solar shield look like? We probably aren't going to build a single structure in the hundreds of, or in the millions of square kilometers. We're probably looking at, as Roger Angel pointed out, a fleet of smaller spacecraft, and they'll probably look something like this. This is a picture of the Solar Cruiser mission that NASA is going to launch in about 3 years. And it's going to demonstrate a number of capabilities that we have to have for our solar shield elements to work. The Solar Cruiser is going to have portions of its sail demonstrate variable reflectivity. In other words, it can adjust its reflectivity on command. That's a very important function for what we need. It's going to have pitch, yaw, roll, momentum control systems on board. Of course, it's a solar sail, so it's propelled by sunlight. It's going to have some onboard navigation capability. It's going to demonstrate the station keeping ability near the Sun-Earth L1 point. And again, for what we want, that's perfect. It's going to have embedded photovoltaic systems. So the systems on board the sailcraft are going to be completely solar powered. And based on conversations with Les Johnson, he says that the aerial density right now for this mission looks like it's about 22 grams per square meter, which is right in the middle of what we were talking about for the optimum point before. Okay, here's the IPCC projections from their latest report. I'm not going to talk about the IPCC. Let's just take their graph here at face value. We have the temperature today, that's that circle, and they have run a number of different scenarios based on greenhouse gas emissions. The very top number is very high rates of emission, and then you have high emissions, and then you have moderate emissions. And then the two lines in the shaded area are low emissions and very low emissions. And what the report recommends is that we greatly reduce real soon our greenhouse gas emissions, and that we invest very heavily in carbon capture technology so that we can keep the global temperature below that 2 degrees C rise, which they feel is necessary. Okay, if we were able to affect a 1 degree cooling with our solar shield that we talked about earlier, and we were able to get this in place by 2060, we can take a scenario where we have very high greenhouse gas emissions and lower the global temperature of the Earth to a number that the IPCC would like us to have, even in the face of very high emissions. And I believe the very high emissions line is where we are currently. And if we do the 1.5 degree C cooling, and we have that in place by 2070, so we have a little bit of time to get it in place, again, we can take the very high emission scenario and bring the global temperature down to what they would consider to be acceptable numbers. And of course, here's the 2 degree cooling. Again, we talked about that. And if we have that in place by 2080, we can maintain the global temperature within limits that the IPCC wants us to have. And playing with lines and a little bit of arithmetic, if we start in 2035 and we have solar sail element launches, 200 to 1,200 Starship launches per week, and continue that to 2080, we can maintain an acceptable global temperature per the IPCC for as long as we need. But one of the objections that has come up to this approach is, yeah, but if you have that many launches, isn't that going to affect the environment in itself? And I couldn't find anything on SpaceX Starship, but I did find something on Skylon. This is, again, a reusable launch vehicle that the British are looking at. It burns hydrogen. And this environmental report assumed that you had 100,000 flights per year. It burns hydrogen, so it deposits a lot of water vapor in the stratosphere. Water vapor is a very powerful greenhouse gas, but doing a little bit of numbers, it looks like the cooling effect from the solar shield is far greater than the warming effect from the additional water. Well, one thing that surprised me and here I'd like a little bit of help, is nitrous oxide production apparently results from hypersonic reentry of vehicles like this, and certainly like Starship, because the shock wave apparently has enough energy to break up molecules, and when they reform, sometimes you get nitrous oxides. Nitrous oxides are very damaging to the ozone layer, and this report said that with the Skylon vehicle at 100,000 launches per year, you're going to erode the ozone layer by 0.5% per year. Now, can we reduce this phenomena? Again, I'd like help on that number or that question. This is kind of new to me, and I haven't really had a chance to dig into it too far. But at the very least, this would argue that rather than direct launch from Earth, we need to start thinking about building the infrastructure in space to utilize lunar or asteroidal resources to fabricate the solar shield elements and then launch them from there. I think that would get the launch rate down significantly. If you go to an environmentalist website, one of the designs you can get on your t-shirt is this, Plan A, because there is no Plan B. And sometimes it's called Planet B. But what I want to argue is that we have a viable Plan B in the offing with solar shields. And that's because of a number of factors. Launch vehicle costs are really, really coming down. Musk is promising he can get launch costs with Starship down to $20 a kilogram. That seems a little bit aggressive, but it's far, far, far better than what we have now. We talked about the fact that most of the technology we need for these solar shield elements are going to be demonstrated in about 3 years with the solar cruiser launch. So we're not too far from having all the technology we need to begin to develop and build and launch solar shield elements. And motivation, there's a lot of motivated people who want to deal with climate change and global warming. So if we could tap into that, I think we have a viable Plan B. So Plan B, the solar shield concept, we can protect our biosphere even in the face of very high greenhouse gas emissions rates for really as long as we want, as long as we continue to launch these things. It buys us time to achieve a carbon-free economy. The IPCC report is really talking about radical reductions in the next decade, and very high, or what they also want is very high investing in carbon capture technology. So rather than trying to do all this in a decade, this will buy us time, a century or two, to more leisurely transition over to a carbon-free economy if that's what we would choose to do. And incidentally, I think it also gives us the key to the solar system, because we will have demonstrated the ability to build space-based infrastructures. Not sure what that is. Okay. And finally, I just want to say that one group that's actually looking into this potential or this option is the Planetary Sunshade Foundation. There's their web address, and you can check on them to see what they're up to. And they're also looking for volunteers. If anybody can contribute, feel free. So really, that's what I got. If we have time for questions, okay.
Great, thank you, Ken. First question, would it be less massive to put shields in Earth orbit, taking advantage of them being closer to the surface of the Earth and blocking more light?
The answer is no, because if you have it in Earth orbit, most of the time it's not between the Earth and the sun. So you've essentially got to build a belt that circles the Earth. And looking at the numbers, no, that doesn't work. Now, launch-wise, you might be able to gain from there, but the reading I've done indicates no.
Okay, thank you. Has anyone considered a sort of reverse Fresnel diffraction system to disperse?
Oh yeah,
insulation?
that's in the literature. The problem there is the precision you have to put into the lens is such that it makes it difficult, not impossible, but difficult. And with the solar sail, you're intercepting photons, you're reflecting photons, and with the lens, you're just diffracting photons. So the complexity doesn't seem to really buy you anything.
Great, thank you. This seems like an interesting repurposing question. Do you have any thoughts on using the solar protector to capture energy and, use it for beamed energy?
Oh, yeah. Oh, yeah. We've looked at that very extensively. For time wise, we weren't able to get into it. But yeah, with photovoltaics built into the sail, and given the area that we're talking about, and assume 10% efficiency, and just 10% of the sail is devoted to collecting energy. Turns out you've got like 30 terawatts to play with. So yes, that is certainly a possibility. And that opens up a whole new realm of excitement. Yes.
Great, thank you. Would there be an advantage to building the shields on the moon?
I think so. I think so. Because of the launch numbers that we saw there, it's possible, but it's probably not credible, especially with the nitrous oxide problem. And again, if anyone can help me out with that, how do we reduce the production of nitrous oxides with hypersonic reentry, or is there a way? So if we just we can greatly reduce the numbers of launches if we think in terms of building infrastructure, on or around the moon to use lunar resources. So I think that's probably the best way to go.
Great, thank you. And I guess if we have time, I'd like to actually ask my own question. Would placing a sun shield at the L1 Lagrange point affect current or future spacecraft at that position?
Well, again, we aren't going to be at the current Lagrange point 1. We're going to be significantly sunward of it. And I don't see that there's anyone else who would be there for any particular reason. It might be a good spot to look for solar storms, and we can certainly incorporate that technology in the solar shield, so that if it sees a coronal mass ejection coming towards Earth, it kind of warns us.
Wonderful. Well, we are out of questions, and thank you very much. We got through quite a bit.
Okay, thank you.
Thanks, Ken. And as a reminder, Ken will be running one of the working tracks this evening in one of these 2 rooms. Next, we've got another of our NIAC fellows, Dr. Ron Paladin, who's going to come in and talk about FarView, which is something relatively close by, but could help us do a lot of imaging for interstellar missions. So Dr. Paladin, if you're online.
I am. Can you hear me?
There you are. Great. Take it away. Thank you.
All right. Thank you. Hello, everyone. My name is Ron Paladin. I work for Lunar Resources. I'm the principal investigator for the NIAC Phase 1 study of FarView, an in situ manufactured lunar farside radio observatory. This chart lists my collaborators, my team members. In addition, we have a large number of collaborators across the country helping us with some of the science, some of the robotics, some of the rovers and such. Our study is going very well. We've made substantial progress in all the critical areas and have removed a lot of issues that were causing us problems at the beginning. There are no showstopper issues that have been found, and FarView is actually looking more feasible and more implementable than it did at the time of our Phase 1 proposal. Next chart, please. So what is FarView? Before I actually get into the details, I want to remind everybody that this is a Phase 1 study, so we don't have a whole lot of money, and we're only 40% of the way through the study. So all the information I'm going to be presenting today should be considered very preliminary. Our concept has evolved dramatically over the past few months and will continue to evolve as we flesh out some of the technical details of the study. But FarView is a low frequency, 5 to 40 megahertz radio telescope array. Actually, it's a radio interferometer comprised of 100,000 dipoles distributed over 120 square miles or 120 square kilometers of lunar surface. The observatory is manufactured in situ, utilizing Lunar Resources developed technologies that first extract metals and oxygen from the lunar regolith and then manufacture functional products from those metals. FarView needs to be built on the lunar far side to shield it from Earth's ionospheric and anthropomorphic radio interference that make these observations difficult to do from the Earth. This study is more of a system study than a technology study. We are attempting to define an implementable architecture along with the necessary technologies needed to build this observatory. The technologies themselves are being developed through ongoing funded programs from NASA, NSF, and other agencies. So this study is intended to really just develop and mature the new approaches, concepts, and technologies to extract the metals from the lunar regolith and manufacture from these extracted materials using robotic systems almost all of the materials needed for FarView, including the antennas and the power infrastructure. So why is this important? Well, on the science side, the observations that FarView will make will provide unprecedented insight on the earliest stages of the universe, testing cosmological models. But it will also provide information on solar and solar system magnetic phenomena and may be able to detect magnetic activity in nearby exoplanet systems. But we think the biggest impact will be advancing concepts for in situ resource extraction and for the manufacture of products utilizing lunar regolith. This advancement will have a very broad impact on how we approach building scientific and exploration facilities on the moon, in particular, developing processes and techniques to build in situ solar arrays and batteries. Because the one thing everybody will need on the moon is power. Next chart, please. So a little bit on the science. The large number of dipoles, along with the huge size of the observatory and the lunar far side site, are all required because the FarView's primary science is to probe the pre-stellar dark ages, when the universe was filled with neutral hydrogen and the first stars had yet to form, through to the cosmic dawn when the first stars and galaxies began forming. What we are observing is the 21 centimeter line of neutral hydrogen redshifted into this low frequency band. It's a very faint signal, so we have to really reduce all background noise. Foreground is always going to be there, and that is going to be a big effort of data analysis. But if we can eliminate the Earth's noise source, these observations now become viable and possible with something like FarView. The figure on this chart, for those aren't familiar with the ages of the epochs of the universe, places the dark ages and the cosmic dawn into perspective with the rest of the universe, indicating what's happening in each epoch. And it also identifies with the little red arrows there, the domain where FarView will explore. The key thing to remember is that FarView is a radio interferometer. As an interferometer, it can map the range of spectral and spatial distributions that are necessary to construct a 3D power spectrum map of the dark ages neutral hydrogen. This contains much more information on new physics and what's going on in that stage than we would get from a single antenna. So that was our reason to go with this very large interferometer. FarView observations will actually be done during both lunar day and night. We actually image the entire sky above the horizon every few minutes. The cosmology observations will be done only at night, only at lunar night for the low background. But all the other science can be done during the day as long as their signal is obviously well above the background. So this includes coronal mass ejections, magnetic activity on Jupiter, Saturn, Uranus, Neptune, other things on there. But also, since we image the entire sky, we're hoping to detect some exoplanet systems, and we will almost certainly see a lot of radio transits. So this will open up a whole bunch of new areas of science. All right, next chart, please. So how do we do this? Well, FarView is enabled by two lunar resources developed technologies, molten regolith electrolysis and vacuum vapor deposition. The extraction of materials from the lunar regolith uses the molten regolith electrolysis process to convert raw lunar regolith into metals and oxygen, and then refine them into a high level of purity. This process needs only electrical energy and gravity. No reagents from the Earth, nor any beneficiation of the regolith is required. Our MRE technology is currently being developed through NASA and NSF funding, and it's currently at TRL3. If our programs are successful, it will be TRL5 by the end of those funded programs. But a variant of our MRE technology is actually being used commercially to make steel. So we know the process works. The issue is how to migrate it to the moon. If you want estimates of our production rates, these are very uncertain, but in a year, we expect to generate somewhere around 5 tons of aluminum, 3 tons of magnesium, 4 tons of silicon, 14 tons of iron, and a lot of oxygen from the regolith. Process of manufacturing the dipoles on the lunar surface use our vacuum vapor deposition technique. This is actually a mature technology. It was flown on the Wake Shield facility missions that NASA flew in the 90s and is at TRL8. It's had to be obviously redesigned for our lunar applications, And we're now at TRL5. It's been tested in the lab and are starting to move on to more environmental tests. This process takes the materials extracted from the MRE and actually manufactures the dipole antennas and power cabling directly on the lunar surface. Modified versions of this vapor deposition hardware are also used to manufacture solar arrays and batteries on the lunar surface using some lunar materials, but some materials brought from Earth. The one other advantage of this is the technologies are very flexible, resilient, and adaptable. So our system can evolve as we learn more about science needs, as we mature the technology, and as we develop a better understanding of the lunar environment. Next chart, please. So I'd like to talk to you a little bit about the architecture. Architecture should be very familiar to people who do radio astronomy from large arrays on the Earth, because it'll be composed somewhere between 150 and 200 subarray antenna elements, each containing between 500 and 650 dipoles, distributed across this 120 square kilometer area on the lunar far side, in sort of a core halo structure. The architecture is fairly similar to that of large Earth-based radio telescopes, and the picture in the upper right shows you a notional distribution of the subarrays at the crater Pauly on the lunar far side. The reason we went to this is that each subarray occupies an area of less than 0.18 square kilometers on the lunar surface. An examination of lunar maps has shown us that finding areas that small that are smooth enough for Farview to deposit its antennas should be relatively easy. So how will construction begin? We're going to start by landing, obviously, our regolith processing facility, which consists of an MRE extraction unit, a refiner cell, and an oxygen capture system, and multiple manufacturing rovers. The first day, we will simply deploy and build a power infrastructure for the RPF. On the second lunar day, the RPF will be activated and start producing metals. The RPF and all the manufacturing operations will be done only during lunar days, stopping production at lunar night. The RPF's thermal design allows it to survive lunar night without external assistance, and it can be used to assist other assets to survive the cold lunar night. From the third day forward, we'll be manufacturing subarrays. Construction rovers will transport extracted metal to the build sites to manufacture the subarrays. In parallel, solar array and battery construction rovers will visit each subarray site and build the necessary power infrastructure for each subarray. Since each subarray is independent, science data gathering will commence as soon as the first subarrays are built and powered, growing as more subarrays come online. Data will wirelessly flow from the antennas to the central data processing system on the landers and eventually be transmitted back to Earth. Since Farview is built of lunar materials, servicing and maintenance of the observatory are relatively easy. With this capability and an occasional replenishment of complicated hardware from the Earth, Farview could actually operate for over 50 years. Next chart, please. So what about beyond the moon? Moving past the moon, our resource extraction technology will also work on Mars. As I said before, it will work any place that you can give me electricity and gravity. So a Mars MRE system would be very similar to a lunar application, except it'd be have a little bit more thermal loss due to the Martian atmosphere and convection with the atmosphere. And so we need slightly more power. If you want to power this with solar energy, we'd obviously need solar arrays roughly twice the size of what we would use for the moon. But other than that additional thermal loss and a larger solar array, MRE could easily extract metals from Martian regolith. The presence of CO2 on Mars means there's another way to do a lot easier extraction of oxygen than our technique. So I would not use our MRE process to get oxygen out of Mars, but if we do make metals, oxygen comes out as a byproduct. As for our vapor deposition process, unfortunately, it needs a high vacuum, so it would not be able to work in the Martian atmosphere. Next chart, please. This is my last chart. In summary, I really want to reiterate the potential impact that implementing Farview may have on science and lunar exploration. The ability to land a few hundred kilograms of hardware and then generate tons of useful metals and oxygen per year from the regolith without the need of anything from the Earth will enable materials to, will make available materials to build exploration and science facilities at much lower cost and risk than if everything had to be brought from Earth. Most importantly, the ability to manufacture power infrastructure components that can be used to operate facilities during both lunar day and night will enable much more than just far view. And it will open up new pathways for exploration of the moon and beyond. As I said before, everyone needs power. Similarly for science, we'll open up a new window into the universe, protected from Earth-generated noise. Far view will be far more sensitive than Earth-based facilities at this low frequency and provide exquisite data in a number of areas, the early universe and radio transits, exoplanets, and magnetic phenomena within the solar system. I thank you. Any questions?
Great, thank you. We do have a few questions. Our first question, will lunar dust be a problem either from charging or just coating the antennas?
The lunar dust is actually transparent at these frequencies. So yes, we expect that there will be dust and we will, not, unless it gets really severe, it's got to be pretty thick for it to start impacting antennas. But also one of the things we just started looking at is with the oxygen that we're generating for our rovers, there is a big issue of lunar dust. And so we're looking at basically, is there a way that we can use our extracted oxygen as the equivalent of canned air and spray it on some of the rover parts that gather dust? And our Astrobotic, our rover partner, is very interested in this and thinks this might actually be very useful. So yes, dust is going to be a problem. Thermal cycling is a problem. Charging is going to be a problem. All these, at least right now, seem very tractable.
Great, thank you. What bandwidth would you need to contact back with Earth, and how would that be relayed?
Right now, it's been an interesting evolution. When we first started this, we were looking at something like 10 terabits per hour, which would be very difficult. With a few changes, we got it down to 5 terabytes per day. And we think there are ways to reduce it even further. With 100,000 dipoles, there's no way we're going to be in a low data mode. This is going to take a lot of data. And looking at what infrastructure is likely to be there, obviously, we're going to have at least an optical comm link to either our own relay or to an infrastructure relay. But yeah, that's basically a topic for phase 2 as we map out how we're going to get all the data back.
Thank you. You talk about metal extraction to be used for electrical conductors, but what would you use for insulators and RF generator circuits?
We actually, for the receivers right now, we're looking at probably having to bring some of those components from the Earth. There are parts of it that we can make with lunar materials, but it looks like there are parts that we cannot. Can't give you a really good answer right now, but the lunar surface itself, we think should be sufficient insulation, but that's going to be a more detailed study later. For those who had NIAC phase 1s, you don't get a whole lot of resources.
Thank you. And I'm going to read this verbatim. Wouldn't this be ideal for SETI techno-signature purposes?
I would think so. We've also been contacted, once information has been getting out, we now have been in contact with solar physicist group that wants to actually have us design a much lower frequency, 1 to 0.25 megahertz. And another group that wants us to design a higher frequency, a few hundred megahertz. So this is, again, a very, very easy to modify system. So if there are particular bands that people think we would look at, it's probably not going to be difficult to build one.
Great. And what are the differences of using FarView's distributed architecture versus a single large far-side antenna in a crater?
Basically, we're an interferometer, so we get a lot more information. We image the whole sky. Any dish antenna will be like Arecibo. It'll image a small spot in the sky. But also because of it's an interferometer, we get a lot more information on the power spectrum, which is something we can't get from a single dish.
Great, thank you. And we are out of questions. So thank you, Ronald.
Thank you.
Thanks very much. We appreciate it. And I'll repeat, as I've said for previous NIAC fellows, we hope to see you in person at the 2023 event. But thanks very much.
That would be great. I used to live in Tucson. I was at the University of Arizona.
Great, very good. All right, and believe it or not, we are on schedule. So we're going to take a break now. We should have, okay, this should be the tours. A couple of bits of information. There are some tours on Monday for which, actually, if we can run the That's the right one. If there are some tours on Monday, if you're still interested, there's space available. Clipboards up at the registration desk. There should now be clipboards there for the Birds of a Feather dinner or dinners to be self-organized by you guys on Monday evening. Other than that, we're going to take a quick 30-minute break. There should be coffee back in the Canyon Room, which is the other end of the ballroom. And we will be back here in exactly 30 minutes at 3:20. Questions or comments, come see me and we'll keep going. Thanks, everybody. Appreciate it. Turn my mic up. Is Jerry? There he is. You're right. No, I'd seen you talking to Jeff, and I was going, okay, he's ready to go. And then I turned around and he's gone. So yeah, you're up next. So great, thanks. Okay. Most people came back on time. There's a cluster of hardcore chatters over in the coffee room, and they're not coming, but that's okay. They'll come later. Here's the clicker. We're going to get a quick lesson to Jerry on the clicker. Thanks for coming back. This will be the last plenary session of the day before we go into some other events I'll talk about later. Got 4 hardcore high-tech 20-minute talks coming up here. We're remaining on schedule. I appreciate that. Thank you for cooperating. We're packing an awful lot of information into the day. So with that, with no further ado, I'm going to introduce Jerry Jackson with H-Bar Technologies and talking about antimatter. So great. Jerry, you're up. Thanks.
Good afternoon. So I'm going to be talking about a subject that actually started as a NIAC grant in 2002, and it's been progressing kind of in the background over the years. And in 2020, we received another NIAC grant. So this is kind of my book report on what we did during the last NIAC grant. In between time, it's been funded by ourselves, by Kickstarter, by any means possible to try and keep this going. Okay, so basically, as you can see in this title slide, what we want to do is go from our own solar system to Proxima Centauri to the habitable zone planet Proxima b. In between, we have a Kuiper belt, which isn't shown, kind of on the inside of the Oort cloud. Then we have our own Oort cloud, the local interstellar cloud, the G cloud. And then because the Alpha Centauri system is a trinary with about double the mass of our own sun, we're hypothesizing that it has a similar Oort cloud, with the difference that Proxima Centauri orbits within that Oort cloud. So there might be gravitational disruption, and maybe it's been dissipated or there's a hole in it, who knows. So anyway, the kind of the thrust of, next slide, please. Okay. So the proposed mission is, again, to use antimatter-induced fission for propulsion and onboard electrical power. We're still talking about a 10 kilogram dry mass, so that's kind of the scientific package. And so because we're dealing with something on the order of 10 kilograms, your propulsion system and your fuel and everything else, you want to be on that order of mass. So you don't want a 50 metric ton propulsion system to get a 10 kilogram package to Alpha Centauri. So our entire philosophy has been to come up with a propulsion and power system that is on the order of a kilogram. Okay. So we're assuming a 10-year burn. So there's an acceleration for 10 years. Then there's a separation, and the acceleration stage gets deflected a little bit, and that goes toward the Alpha Centauri binary core and does a flyby of that. And then we decelerate to go into orbit around Proxima Centauri and then around Proxima b. We're assuming two-way communication with both probes. So part of what we're doing is looking at relaxing the spacecraft velocity requirements by doing basically what Voyager 2, Ellen Stern told us about this earlier today, where Voyager 2 had a bunch of scientific returns within a year, 2, 3, 4 of launch. And then there's been this big 30-year delay, and now we're seeing the heliopause physics coming out of it. So in a similar manner, what we're looking at is saying we could go very, very slow, take 100 or 200 years to get to Proxima b, as long as we have some prompt science return along the way. And that's why I pointed out all these intermediate destinations that we can provide scientific return on. Okay, so go next slide, please. So the bottom left graph there shows the amount of antimatter needed as a function of the mission duration or the transit time. So you see it's a very, very strong function of velocity. And so what we're looking at is a 200-year mission with a basically 2% of the speed of light, okay? And so again, there is on the right, you see the Voyager 2, where you have all these Jupiter flyby, Saturn, Uranus, and Neptune. And so what we're looking at, a mission profile that replicates that experience. Next slide, please. So one of the things, so there were a lot of different aspects of this mission that we studied in this NIAC grant. One of them was, prior to that NIAC grant, we had already come up with this way of storing the anti-hydrogen. Okay, you can't store antimatter, grams of antimatter. We were talking about for a 200-year mission, 35 grams of antimatter. Okay, so to do that, you can't have, some sort of magnetic bottle with charged particles. You have to have a molecular antihydrogen, okay, in order to store it, to have good enough density to store it. The problem with that is that you have a vapor pressure, even at a few degrees Kelvin, the vapor pressure is high enough that you would lose all the antimatter over that 200 years before you need it to decelerate. And so what we did is basically built came up with a bottle around the antihydrogen made out of anti-lithium, which contained the vapor pressure. And so because anti-lithium has orders of magnitude lower vapor pressure, the fuel will now survive. And so the idea is that you need then to produce the anti-lithium. And so basically through a series of fusion steps, you can, with all known cross sections and from an accelerator, I'm an accelerator physicist. So from an accelerator physics point of view, we know how to build each of these colliders in order to synthesize that. It's just a matter of putting it together, proving it. We could do it with normal matter at first and then switch the polarity of all the magnets and then do it with antimatter. So that is actually low-hanging fruit where we could start developing the factory using normal matter. And then once we have reestablished an antiproton source in the United States or the world, actually, then we could go and start producing the molecular antihydrogen that's coated with this anti-lithium. Next slide, please. So one of the objections voiced in a past conference from actually NASA people was that how do you know that this fuel form is stable against cosmic rays or other upsets? Okay, so we actually, during this NIAC grant, we actually did a study where we looked at cosmic rays either hitting the matter outside titanium wall of the vacuum chamber that's holding these pellets, or the cosmic rays hitting the antimatter itself. And so the question is, with all these different effects, so when you have a cosmic ray hit a material, you get electrons or positrons coming off the surface. You have nuclear effects, which means you have ions coming off, secondary emission, all these various effects, okay? And so by putting all of these in a loop, and you could ask yourself, okay, is the gain factor greater than 1? So if you have an event on one of the surfaces that spews particles into, let's say, the antimatter, it then reacts and spews particles back. If the gain is greater than 1, then you'll have a runaway and you'll lose the fuel. Okay, so we did this analysis and we could not find a scenario in which that gain factor is greater than 1. So our preliminary conclusion from this is that it's actually stable. Next slide, please. So alternative deceleration techniques. This was, we had the core using the the antimatter to induce fissions. The fission daughters are provide the momentum transfer to get thrust. But we also, during this grant, looked at, are there other things that we could do rather than just this direct thrust approach? So could we actually generate electrical power and then use that electrical power to generate some sort of drag against the interstellar medium? And I can't read my slides because we have all these chats going on. Okay. So we looked at, for instance, John Slow's plasma sail. Jeff Grayson led this. He did a lot of work on this, very good work. And that's still ongoing. But basically the idea is opening a parachute, right? So it's kind of the classic way of transferring kinetic energy of the spacecraft into some other medium. Next slide, please. Okay, so prior to this grant, I had hypothesized that it might be possible for a highly charged spacecraft to deflect the electrons in the interstellar medium in order to generate a deceleration very similar to a charged particle going through material undergoing DDX. So if you go back and look at history, the first calculation of this was done by Niels Bohr, and he did this in a classical regime. And so I'm calling this Bohr deceleration. Okay, and so the idea is that very similar. In the case of going through a material, you have you have what basically Avogadro's number per cubic centimeter. In the case of the interstellar medium, you have 1 electron per cubic centimeter. So orders of magnitude lower density, but you have also, instead of stopping in a millimeter, you have millions of kilometers, okay? And so the two scales offset each other. And so it's possible that there is a solution where by charging up the spacecraft enough, you could actually deflect enough of the electrons in a big enough radius around the trajectory of the spacecraft that you could couple your kinetic energy of the spacecraft into the kinetic energy, remnant kinetic energy of the electrons that you pass. The problem with this calculation is that it actually violates all the assumptions that go into classic DDX calculations, the Debye shielding calculation, all the sort of classical plasma physics calculations that you would approach. It turns out because you're well above the velocity of the interstellar medium distribution, and there's causality because you're near the speed of light, more or less. There are a lot of effects, and also because you're now accelerating the electrons, instead of having a 10 to the minus 19 Coulomb charge going through this material, you have, let's say, a spacecraft charged to a kilovolt. When you do that, you have, so the graph up in the upper right shows, it's kind of like a movie. So the top left of the line is the spacecraft, the bottom right portion of the line is where a given electron is. And instead of the normal assumption where the electron doesn't move as the spacecraft goes by, even for a range of 1 meter, the electron actually moves across the trajectory of the spacecraft. And because you're dealing with very high voltages on the spacecraft, as the particle falls into the potential well of the spacecraft, it actually is reaching velocities where the electron starts to radiate. And so it's no longer a conservative system. And so the entire approach to doing this calculation is actually much more complex than you originally would think. I mean, a lot more work has to go into this. And this is just the beginning of, I think, a longer discussion. Next slide, please. So the core of a lot of what we did was looking at what other physics can we do, or space sciences can we do along the way. And so here's kind of a map for a 2% terminal velocity or drift velocity through the interstellar medium, what you could do early on in the mission. So for a 10-year acceleration up to 2% of the speed of light using the rocket equation, all that, you get this profile of mission duration and spacecraft distance. So in about 18 months, you get to the current location of Pioneer and Voyager. Within a year and a half, you get to the gravitational gravity lens. A little over 2 years, you get to the outside edge of the Kuiper Belt. And within 3.5 years, you're into the Oort cloud already. And so the idea is what could we do with the Oort cloud? Because obviously the Oort cloud is giving you 30 years of science there. Okay, so next slide, please. So what we said is, okay, what if we said, you take the sort of what people think they know about the Oort cloud and say, okay, on average, what would be the incident rate within 0.1 AU of the trajectory of the spacecraft? And it turns out you would, the spacecraft at 2% of the speed of light is traveling at 1 AU every 5.6 hours. And that gives you about 450 rendezvous per Oort cloud, because we have a second Oort cloud around Alpha Centauri. And so over 30 years, it's about one a month. So you would expect about once every month, you would have a Oort cloud object within 0.1 AU of your trajectory. So the question is, and so the original goal was, could we detect these objects early enough so that we could send out some sort of chip craft and intercept and do a flyby very similar to New Horizons did with the Kuiper Belt object. Now, I forget the name of it, but the problem is that for the case of, for instance, New Horizon, it knew ahead of time where that Kuiper Belt object was. Okay, we don't have that luxury. So the spacecraft has to do long range sensing to tell far enough in advance where these objects are so it could send out a chip craft, a 1 gram chip craft, and intercept it and get a picture. Next slide, please. So Jeff and I looked at dozens and dozens of different approaches, okay? So one of the approaches we looked at is stellar occultations. And so for instance, there's on the left there, those are the predicted occultations for Proxima Centauri. Okay, and so, you know, the star field looks from the Hubble Space Telescope looks like you have a lot of stars there. Okay, but when you zoom in for the magnitude of stars that are observable by Hubble, they're actually very far and few between. And so we concluded that we're not going to be able to do it by looking forward. So at that point we said, okay, why don't we relax our criterion and say, what if we just do a survey of Oort cloud objects and just do measure density distribution without trying to do a close flyby? And so you can say, okay, instead of looking toward Proxima Centauri, why don't we look toward the galactic center or look toward a extended illumination object such as a nebula? And that should provide us more of a broad light spectrum behind so that we can see a more continuous occultation. And we have yet to come up with a solution where that works. Next slide, please. So one of the things I looked at was, what if we
Jerry, just so you know, you're at about 2 minutes, which would be your question period. So
yeah, this is like the second or third from this end slide.
okay, you're almost out of time. Thanks.
Okay, so we looked at, well, could we actually measure the Oort cloud temperature and therefore distinguish the Oort cloud objects from the cosmic ray background? Next slide. And so if you look at the cosmic ray spectrum and the expected black body radiation of the Oort cloud objects, looks like we have about 3 orders of magnitude contrast. And we've come up, some summer students came up with a very lightweight telescope, and we're looking at making, for under a gram, a 2 or 3 meter telescope. Next. I'll just skip over this. The green says we did find something feasible. Actually, we did not find something feasible. I left out the word not. Okay, next slide. And this just, you can read this, it's just our future work. Thank you.
Great.
All right, we do have a couple of questions. First, yeah, all right. The same delta V could be used to either decelerate at Alpha Centauri or to double the velocity and thus halve the trip time. For a 200-year trip time, I would suggest that you'd be more interested in having the trip time to 100 years than in decelerating to get better exploration results, but taking another century to get there.
So the question is, what's the hurry? Okay, well, none of us in this room are going, even if it's 100 years, none of us are going to be around to see it. Okay, and so I like to point out that, you know, there are cathedrals like York Minster Cathedral in England that took 250 years to build. Okay, as a species, we have built objects that have taken several generations. So the idea that somehow we have to go fast, I'm going to challenge, okay? I don't think that's actually true, as long as the funding agency or the individual, whoever funds this, could get some results early on, very similar again to Voyager.
Might as well call it here.
And with that, appreciate it. Jerry, thanks very much. And Jerry will be around for more questions during the break in the poster session, I'm sure. Okay, we're switching to a Zoom speaker. Mike McCullough was going to be here from England, but it's kind of hard to cross international borders these days. We do have some Canadians here. Thank you for making it, but I think crossing the Atlantic was just a bit of a challenge. So Mike, I saw you on the Zoom. If you have audio turned on, say hello.
Hello.
There we go. Dr. McCullough, it's yours. Take it away. Thanks.
Great, thanks. I'm glad to be here. So I'm going to obviously talk about how I think we can get to Proxima Centauri in about 12 years with new physics. So of course, as been said before earlier, Voyager 1, our fastest probe, well, maybe except for New Horizons, is going to take about 70,000 years to get to Proxima Centauri. So I think we can do rather better than that. I'm going to introduce a theory called quantized inertia that I proposed, give you the astronomical evidence for it, tell you about DARPA-funded tests for thrust, and then give you a proposal for a 12-year mission to Proxima. Next slide, please. So just to show you where I started, this is a galaxy, the Andromeda Galaxy, and this is a problem I started thinking about. We can look at the Doppler effect and the speed of stars going around a galaxy and work out the centrifugal force, the inertial forces, and they're extremely large, much larger than the gravitational force pulling them into the center of the galaxy, given the visible matter that we can see. So the problem is that galaxies should be exploding, but they aren't. So next slide, please. Astrophysicists tend to add dark matter to galaxies to boost the gravitational force to hold the stars in. But I don't like the solution because it's very arbitrary and it doesn't seem scientific to me. Okay, next slide, please. So I've suggested an alternative model for inertial mass called quantized inertia. So it works like this. You have an object. You have an object, for example, this black ball in the center, and imagine it's accelerating to the right. And quantum mechanics tells us that it sees Unruh radiation, which I've shown on this diagram with red, because it's very much like thermal radiation that impinges and pushes on the object. Also, at the same time, relativity tells us that behind the object's acceleration, a horizon forms. And I've shown that with this black area here. This light from this black area can never catch up with the object because it's accelerating away. So quantized inertia, the essence of it is assuming that this horizon damps the Unruh waves. So I tried to show that by showing this blue color here. So the Unruh field is warm in front of the object, it's cold behind it. So you get a pushback. There's more radiation hitting the object from in front than from behind. So it pushes back against its acceleration. And I showed in a paper here in 2013 that this looks like inertial mass. Okay, next slide, please. But that's not the whole story. If the acceleration is extremely low, as shown here in this picture on the right, then the Rindler horizon, the horizon I showed before, moves back so far that it's about the same distance as the cosmic horizon all the way around the object. So now you can see the Unruh radiation is hot in the center but cold at the edge near the horizon. And this means that this imbalance that we had before has gone. So this theory predicts that inertial mass will collapse for very low accelerations. And I showed this in a paper back in 2007. Okay, next slide, please. This means that, well, this is exactly what we need to explain galaxy rotation, because stars at the edge of galaxies are accelerating very slowly. So the inertial, in the theory, the inertial forces they see reduce, and it turns out that they reduce so they're exactly balanced by gravity. So it works very well. And I can show this using the data. Next slide, please. If you look at the expected acceleration of galaxies shown here along the x-axis and the observed acceleration on the y-axis, the data, which I got from Professor Stacy McGough, is shown by the gray squares, and the theory goes right through them. It's a dashed line here. So it works very well, and it works very simply as well. So the equation is shown on the right. The velocity to the power 4 is equal to 2 times gravitational constant times the visible mass of the galaxy. So you don't need dark matter, times speed of light squared divided by the Hubble diameter. And I showed that in a paper in 2007. So the theory predicts galaxy rotation very simply and without the need for dark matter. Okay, next slide, please. But not only that, there's direct evidence, because if you look at a galaxy, in the center, the stars are accelerating rapidly. So they see short Unruh waves, as I've shown on the bottom with this red sine wave. As you go up to higher radii, the Unruh waves lengthen, so you can see that here. And at exactly the radius at which the acceleration of the stars is such that it produces Unruh waves the size of the cosmos, then that's exactly the point at which the galaxy starts to misbehave. So that's very direct evidence for quantized inertia and for Unruh radiation. Okay, next slide, please. So the great thing is that if we understand inertia, then we can control it. So if you imagine an object shown here on the right with this black circle that has something inside it accelerating very rapidly, then it will see Unruh radiation. So I've tried to show that with this red and yellow here. And then if the acceleration is so large that the Unruh waves are short enough, then we can damp them with a metal plate by putting a metal plate above this object. And I've shown that here with this gray area. This will then damp the Unruh waves. So I've shown that with the blue area. And there will now be, well, in a sense, we've created an inertial mass for this object acting upwards, or an inertial force acting upwards. So the object will tend to move up, or if you like, down this Unruh radiation gradient. There'll be more radiation hitting it from below than there will be from above. So this is the idea of a horizon drive, this metal plate acting like a horizon. And it's very useful because usually to move something up, we have to expel things out of the bottom very fast, the rocket idea. This doesn't require any propellant. So I discussed that in a paper in 2018. Next slide, please. So I was contacted in 2018 by DARPA, and I applied for funding and was awarded $1.3 million of it. And the aim of the project, the ultimate aim, is to show whether we can get thrust out of the theory to either thrust in space or even launch. Okay, next slide, please. So one way to get force from quantized inertia is looks like this. So the schematic on the right, we have a laser. We fire laser light into a fiber optic loop. So it accelerates around the loop very fast. And the idea is that it should see short, hot Unruh waves. So I've shown that with the red. And then we put a metal plate beneath it, and this should damp the Unruh waves there. And the loop should then try to move down the Unruh radiation gradient. So it should move down. And the theory predicts that the force should be, as shown here, pi times the power in watts that you put into the laser. The Q factor of the loop, which is the number of turns in the loop, the radius of the loop, and then divided by the speed of light times d, where d is the distance between the loop and the metal plate below it. So next slide, please. So I've funded a team in Madrid, Spain, at the University of Alcalá under Professor Perez Diaz, and they have been doing experiments, and they have some positive results. So here's the most interesting result is shown in bold here. So the first row here has very low power, but when the power was boosted, so the power into the laser was 0.129 watts. The radius of the loop was about 15.2 centimeters. Quantized inertia predicts that there should be a thrust of about 6 micronewtons, and we saw a thrust averaged over a few experiments of 10 plus or minus 6 micronewtons, which is consistent with it. So one point here is that this represents a force to power ratio of 0.08 newtons per kilowatt, which is better than the ion drives used in satellites at the moment. And it's doing this without fuel. So this just requires electricity, energy from solar panels, for example. Okay, next slide, please. So part of the DARPA project, well, phase 3 of it that we're now in, is aimed at enhancing the thrust. So there are several ways to do this, and one way to do it would be to use, instead of normal glass, use fluoride glass, which has from 10 to 100 times the transmission of normal glass. So we could do that, and it would also be very beneficial to use, instead of a coil of loops, so have the light going around a coil, to have simply one loop. But if we do that, we'd have to have a whispering gallery, what's called a whispering gallery resonator. And a good example of that is St. Paul's Cathedral in London. If you stand in a gallery of St. Paul's and you say something, the sound travels around the gallery very effectively and keeps going around the circumference like that. And that's because the sound waves are exactly the correct wavelengths, that they do not self-interfere when they come around again. An integer number of waves can fit within the circumference. And if we can do this with light, the transmission would be very effective. So that's one aim that we had. So it's possible that we could improve the 0.08 newtons per kilowatt to, well, theoretically 8 newtons per kilowatt, which would be very good. This is getting close to the thrust to power ratio that we need to start launching things or levitating them. And it certainly enables interstellar travel, as I'll show you now. So next slide, please. Okay, so the idea is to use a safe 400 fission reactor. I'm sure there are different alternatives available, but this reactor was pointed out to me by Travis Taylor. It's about half a ton, and it provides 100 kilowatts of power. And then you have the mass of the QI horizon drive, which should be fairly light, about 5 kilograms. Camera shield and antenna, I'll show you the design in a minute, 50 kilograms. So the total is 567 kilograms. And with relativity at half the speed of light, that would go up to about 654 kilograms. The force produced by the reactor and the horizon drive would be about 800 newtons. And that would give you an acceleration of 1.3 meters per second. So the idea would be to accelerate at that acceleration for 3.7 years, up to half the speed of light. The distance traveled would be 1 light year, and then cruise for a bit at half the speed of light for 4.6 years, and then decelerate for about 3.7 years. So this means that we could get to Proxima Centauri in 12.3 years from an Earth point of view in the Earth frame, and 11.7 years in the ship frame. Okay, next slide, please. So this is an initial spacecraft design. So in the center, you can see the laser loop. So the laser is here producing 1.8 kilowatts. It goes into the loop, the whispering gallery loop, and it's not entirely clear how we can do this yet, but we need to somehow get the light to stay within glass. So this would be the whispering gallery resonator. Then next to that, this gray area shows the Unruh shield. So this will damp the Unruh field in front of the loop and pull it to the right. And when we want to slow down, this will be rotated round to the other side, and that will then pull it back. So obviously there's a shield to shield it from interstellar dust, and research shows that you need at least about 4 centimeters of aluminium to do this, but I've shown a sort of matrix here, spread out a little bit. The reactor is here, this red area. There's a camera and an antenna as well. So this is one of the problems, how to get the information back from Proxima Centauri. There's a freeze transmission equation, and it turns out that it may be possible if the receiving area is about solar system scale. So we need something like an expanded deep space network and use very high frequencies of radio waves. Okay, next slide, please. Okay, so a summary is that quantized inertia explains inertia for the first time. It's an alternative to dark matter. It's got very good astronomical evidence behind it. It predicts a horizon drive, what you might call an electric rocket, fuel satellites, and it enables interstellar travel. So we have tests showing QI thrust of 0.08 newtons per kilowatt. That's theoretically enhanceable to 8 newtons per kilowatt. And we're going to try and do that in the next year with the DARPA funding. And QI enables travel to Proxima Centauri in 12 years this way. Okay, so any questions? Thank you very much.
I think we have time for a quick one here. So the submitted question is, doesn't the UNRWA radiation bathe the object uniformly and not just in the direction of movement?
Yes, it does, but the idea is that the acceleration in the laser loop is so great that the UNRWA waves are short enough that they can be damped asymmetrically by a metal structure, by a metal plate placed on one side of the object. So normally they would bathe it uniformly, but we're making an asymmetry in the field.
Does the UNRWA shield absorb the extra momentum?
Well, in a sense, it produces momentum because it's, in a sense, where we're introducing an inertial force.
Okay, that's time.
We start 2 minutes late.
Okay. Have you thought about beaming the energy to your drive instead of using an onboard fission power source?
Oh no, I hadn't thought of that. That's interesting. I'm not sure how possible that is, but yeah, that's an interesting suggestion.
Why have particle accelerators not seen this effect in beam dynamics?
They have. A paper was published this year by Lynch, somebody called Lynch, L-Y-N-C-H, and they have seen UNRWA radiation in the deceleration of positrons hitting crystal targets. So it has now been seen.
Would this produce any kind of radiation coming out of the vehicle?
It would the UNRWA radiation would only be perceivable by the accelerating objects within the vehicle, not from outside.
Is that it, Stephen? You got one more? I've got 2 more, but all right. As your velocity becomes non-negligible compared to c, does the cosmic horizon appear asymmetric? This requires more watts per Newton as you go faster?
Yes, good question. Would it become asymmetric? Yes, it would certainly change shape, but I don't know exactly how. That would have to be modeled.
How well does quantized inertia do at explaining galaxy clusters, bullet clusters, CMB peaks, and other non-rotation curve evidence for dark matter?
Yes, well, the bullet cluster, it explains that because the galaxy clusters are rotating, and quantized inertia predicts that light will bend as it crosses a rotation axis. So if you look at the bullet cluster, you see that the apparent dark matter is at the 2 ends, which would also be predicted by quantized inertia.
Okay, that's all that we have time for.
All
Thank you
right.
very much.
Thank you.
Dr. McCullough, thank you. Appreciate it. Absolutely fascinating. And I'll repeat as I'm repeating for all our remote participants, we hope to see you in person in 2023. So as we're all able to get on airplanes again. With that, we have a Gedanken experiment. I think I pronounced that correctly by Matthew Gorbin. So Matthew, come on up.
Hi, everyone. Thanks for having me. I'm going to just make sure that this clicker is indeed working. Okay. So I'm Matthew Gorbin, and I'm a fourth-year PhD candidate studying under Professor Gerald Cleaver in the Baylor University Department of Physics. Today, I'm going to be introducing a research proposal that uses controllable mass objects to induce linear motion on an otherwise stationary harmonic system. So like I was just mentioned, this is a Gedanken experiment or thought experiment. So much in the same way that we use exotic energy and exotic matter to study the physics, the underlying physics of warp drives and wormholes, I'm going to be using these objects in which their masses can be changed. And these are theoretical objects for the time being. And I do go into some more details on some mechanisms for changing an object's mass in my paper. But for the purposes of this talk and due to time constraints, I'm merely going to address the physical system in which using these objects allows for induced motion on a harmonic system. So looking at a simple example of a hanging controllable mass object, or CMO for simplicity, attached to a spring in a gravitational field, we see that this object can be adjusted from a higher mass state in red to a lower mass state in blue. And because the higher mass state has more interaction with the gravitational field, its equilibrium position relative to the lower mass state will be displaced below it. And so we're going to use this concept here in order to show that we can get driven motion in a harmonic system by simply changing the masses of our object. So we are going to initially start our system in the higher mass state at rest in its equilibrium position. We are then going to change the mass to the lower mass state. And we see that now, after we've changed the mass of our system, that lower mass state has been displaced relative to its equilibrium position. It's been displaced delta x, where delta x is simply the distance between the higher and lower masses equilibrium positions. So after this mass change has occurred, the system undergoes simple harmonic motion with amplitude delta x and will move upward to its maximally compressed extremum position, delta x, above the lower mass equilibrium position. At this point, we will then change the mass back to the higher mass state. And we see that we are again displaced relative to our equilibrium position, except this time we are displaced 2 delta x relative to the higher mass equilibrium position. At this point, the system will move downward, again undergoing harmonic motion to 2 delta x below that higher mass equilibrium position, where we have then completed one full cycle of our system. And we see that by only changing the mass of our object, we are able to displace the system and cause driven oscillations. And this can be repeated as many times as necessary. And every subsequent cycle, you'll see that we have an additional 2 delta x displacement below the previous position itself. So before I go into the more complicated 2CMO 1 spring system, I want to address fundamental conservation laws. In terms of the conservation of momentum, this one's actually pretty straightforward. Because the masses are changed at the extremum positions and because the velocities are 0 in the lab frame, the mass can be changed at will. We know that any stationary object, regardless of their mass, will have identically 0 momentum. So it doesn't matter if you change the object of change the mass of a stationary object, it doesn't change the momentum of the system. In terms of the conservation of energy, this one's a little bit more complicated. So we are violating the conservation of energy initially. This is because we are changing the mass of our system. And if it is a closed system, we are seeing a total energy change of this closed system. However, this should be reassuring because what this means is that unless we input energy into the system to facilitate the mass change and cause these driven oscillations, we will see violations in energy. This means that we do not have a perpetual motion machine, assuming that we've inputted energy into the system. We aren't getting something from nothing. Again, this should be a reassuring fact. So now we're going to look at the 2CMOs 1 spring system, where we're going to have 2 controllable mass objects attached via a spring, and this is going to be in free space with no additional forces like gravitational forces interacting with the system. So the equations of motion for this system are as followed. They're the standard equations of motion for any 2 object, 1 mass system. And we can solve these to get the displaced positions as a function of time. Notice the initial conditions. For this example, I'm going to say that the spring has been starting in its maximally extended position, where we have big X sub L and big X sub R as the initial displaced positions of the left and right mass. We've also imposed the condition that their initial velocities are 0. This is to address the conservation of momentum that I just discussed. And because these are both 0 at identical times, we can then change the masses of these objects simultaneously without violating any of the conservation of momentum. And again, we are inputting energy into the system when we change this mass in order to avoid violating any of the conservation of energy. It's important to note that these are the displaced distances over time, not the real positions. And if you simply wanted to calculate the positions of these masses, all you would need to do is incorporate the initial spring length into the system. We can use these equations of motion to calculate the extremum positions of the system. So these are going to be the maximally extended and the maximally compressed positions as we cycle through this harmonic cycle. So we see that we start at X sub I, and we will then, which is going to be the initial extremum position. In the case in the upper right-hand corner, we see this is going to be the maximally extended position. We will then evolve the system to its midway extremum position, XM, which occurs halfway through one cycle, tau. And then assuming that no mass change occurs during the system, the cycle will just oscillate back and forth between XI and XM. Again, this is standard harmonic motion. However, what happens if we do incorporate mass change? Well, the basic system goes as follows. We will start in our initially displaced position, X sub I, at rest, and we will allow the CMOs to be released and evolve to its first midway extremum position. At this point, we will be changing the masses such that the left mass, ML, will go to an ML prime, and the right mass, MR, will go to an MR prime. At this point, we will again allow the system to evolve to the next extremum position. And it's important to note that this is essentially the exact same as just starting a brand new cycle of XI using the previous cycle's midway extremum position with the new masses. Then at our secondary extremum position, we will change the masses back to their original values. And at this point, we have completed one full cycle of the system, which, like the hanging mass system, can be repeated as many times as necessary. Now, the really interesting part about this system that we see is that after one full cycle, both of the masses have been shifted along the spring axis by the same amount. This will vanish if you assume that MR and MR prime are identical and ML and ML prime are identical, which is the exact same thing as saying that we don't have any mass change of our system. This can be simplified in one of two ways. We have a single mass changing. So in this case, we have the right mass is the only one changing and the left mass remains the same. We can also see a simplified system where the mass values have been switched. So in this case, MR becomes ML and ML becomes MR at the extreme positions, and then vice versa as we run through the cycle. And this is going to be the case that we're going to be analyzing. So we can see here that over the course of one cycle, after having changed the mass and going back to our original mass states, after we've gone from our midway extreme position to our brand new initial position, that we have shifted our system by a delta X, where again, like I said, this can be repeated as many times as necessary. In this case, the heavier mass is going to be twice as heavy as the lighter mass. And so where's the origin of this mass shift coming from? Well, it's a lot more evident when we look at these three different examples. So we can see with focusing on the bottom case that the heavier mass in red is going to effectively remain stationary in our system. The heavier mass is pushing and pulling the lighter mass through space. I like to say that this is inchworming its way through space. So we can see that when the heavy mass is leading the lighter mass in its maximally extended position, it will pull the lighter mass towards it. Upon mass changing, it is now trailing the lighter mass and will push it away. This is really the origin of that mass shift. And we can then use this shift value as well as the time it takes to complete one full cycle to calculate an effective velocity of our system. And it's important to note this is an effective velocity of the system. The system itself isn't gaining velocity. We aren't gaining momentum. Otherwise, we would be violating the conservation of momentum. We would have started from a stationary state and then gained velocity. It's merely moving through space at this rate, and that rate is induced by the mass shift that we see over the course of one full cycle. We can then look at this velocity and using some simplification techniques by addressing a mass ratio M, where M is merely the heavier mass over the lighter mass. We can rework this velocity and we can analyze the limit where the heavier mass is much greater than the lighter mass, like I just mentioned in the previous slide. And we see here that the velocity is only going to be a function of the spring constant K, the initial displaced distances, and the smaller mass value. Because again, this smaller mass is really the one that's driving the motion of the system. It's doing all the movement. And so we can look and see how much this traverses each length. And so again, looking at this animation where the heavier mass is 100 times as heavy as the lighter mass, this delta XM that you see here on the right-hand side is going to be the distance for every half cycle that each mass moves. So we see in this upper limit that the lighter mass is doing all the movement. It's moving twice the initial displaced distance of the system, and the heavier mass is not moving at all. And as this mass ratio decreases towards unity, then we would see that these numbers slowly approach each other. So then how fast can we move with this system? Well, we can see that our velocity can be scaled regardless of mass by simply changing the spring constant K and the initial displaced distances, where the initial displaced distances are effectively the input energy required to drive the system. So what do we want? Well, we want high spring constants, noting that springs sum together in parallel for easy scalability, and we want large displacement. So we need to use long springs. So if we want to go a meager 10% of the speed of light, then we see that for low spring constant values, we need incredibly large distances. And this should make sense. We're trying to go 10% of the speed of light. We need incredibly large amounts of energy in order to move this speed. We're talking distances on the order from the Earth to the moon. Now, if we wanted to work with a little bit more realistic distances, so for example, here, if we want to go about 1 kilometer spring displacement, we would need spring constants on the order of 10 to the 9th kilograms per meter squared. Again, this is going 10% of the speed of light. And if we wanted to go a little bit slower, so we're talking 500 meters per second, which is the speed of Voyager 1, and we have a lot more realistic spring values and spring constants that would certainly be achievable with today's technological capabilities, assuming you can overcome the large hurdle of changing an object's mass. So here, if you want to work with spring displacement distances on the order of around 50 meters, you would need spring constants around 100 kilograms per meter square. So at this point, I'm going to be ending my talk on some future work. These are going to be points that I'm planning on addressing in future papers in this series that I'm writing on how to use control of mass objects to induce linear motion on an otherwise stationary harmonic system. So thank you for your time, and I will now take some questions.
All right, so we've got about 5 minutes left, so we can, keep throwing questions at you. So keep them coming, folks. How do you change the masses of your objects without violating the conservation of matter?
So really what we're addressing is the conservation of energy. So what you would effectively need to do is input an amount of energy equivalent to the mass change of your object. So again, like I said, these are theoretical objects. So there are certain systems like the Casimir effect that you can see mass changing of your object. So for example, if you have two parallel cavities in a vacuum and they're really close to each other, we see that the interior of the cavities gains an effective negative energy of the system. So if you're able to manipulate the boundaries of these cavities, you would effectively be able to induce a larger Casimir effect, for example, and you would then effectively lower the mass of your system. And you should see these calculations have not been done, and I'm planning on it because changing the boundary conditions of the Casimir effect is sort of an emerging research field. So you see that the effective energy it takes to change the boundary conditions should be roughly equivalent on the same scale of the mass change that you see with the enhanced Casimir effect. So you are putting energy into the system equivalent to the energy change of your object itself.
Is one of your baseline assumptions that the masses are such that they make the spring mass negligible?
Yeah, so I'm assuming zero spring mass here. That would not really affect the actual motion of the system if you assume the spring mass, because again, all the mass change is going to be in the objects themselves and not associated with the spring.
The Gedanken experiment assumes instantaneous mass change. Has non-instantaneous change been considered?
Yeah, that is a fantastic question. And that is one of the things I'm going to be addressing in some of my future papers in this series. This does assume an instantaneous mass change. And so if we, this analysis that I've done assumes that, so I've not completed those calculations regarding a mass change that may occur over a non-instantaneous period of time. So look forward to future papers on that. But this does pose an interesting question about how we can actually create a physical system, because, for example, going back to the Casimir effect, the boundary condition change would not occur instantaneously. It would occur over a short amount of time. So if we were to try to manipulate this system using real world examples, we would have to account for the length of time it takes to change that mass. However, that calculation hasn't been done, and that's actually what I'm planning on doing after I submit this paper.
How do spring constants in this compare to material tensile strengths?
That's actually, again, a really great question. And I had a very difficult time trying to find real world spring constant values associated with springs. I wanted to get some nice examples in the paper, but you don't really see real world springs give you, here's a spring constant value. Those numbers aren't really presented when you're looking at springs. So I haven't gone that far yet. Again, I've sort of addressed the theoretical system. And as you can see here, I'm going to be looking at real world systems by using the Casimir effect and using actual spring constant values, for example. So I'm not quite certain about that information at this time, but it is something I am planning on addressing.
As a materials guy, you should talk to me about that afterwards.
All right, well, I was planning on saying hi later, so that's great.
While you claim there is no violation of momentum, since mass changes while masses are at rest, an observer in a reference frame translating at constant speed, which is an equally valid reference frame, would see a spontaneous change in momentum. How can you avoid this violation of conservation of momentum?
That, along with things like relativistic effects of the spring, are things I need to investigate further. Again, I've assumed that this mass change occurs locally in the lab frame. So that is something I need to address in the future. But as of now, that is not something I've calculated.
Yep, that's it.
All right, we're on time. Matthew, great job. Thanks very much. Appreciate it. Thanks, cool. I'll give that to the AV desk, your last. Okay, and our last in our series of NIAC fellows who didn't make it to Tucson is Chris Morrison. I actually saw Chris's talk at the NIAC Symposium online. I forget, Tuesday, Wednesday, I don't know what day it is right now. But I saw a version of this earlier this week and it's awesome. So this is our 14th technical talk of the day. I know we're loading a lot of information onto you. We do get a break after this. So one more talk and then I'll explain how the evening is going to go. But Chris, take it away. Thanks.
Thanks. Just checking that you can hear me.
Yes. Yes.
Excellent. All right. So next slide. So extrasolar objects are obviously objects from outside the solar system, but the good news is that they're not very far away. They fall into the solar system very close to the sun. So it's not a problem of distance, it's a problem of speed. And in general, a lot of what I'm going to be talking about won't be relativistic. It'll be more like 100 kilometers per second, which is obviously a great improvement on state of the art when you talk about things like Voyager leaving the solar system at 17 kilometers per second at delta V. We're talking about objects that are leaving the solar system at closer to 30 or 40 or maybe 50 kilometers per second at delta V. And the first one of these objects we found in 2017, Oumuamua, brought on a lot of speculation about aliens, because if you were an alien species and you wanted to come visit star systems, it would actually be a pretty good orbit to come very close in and check it out. A few years later, though, we found Borislav, and now we tend to think that we're going to find a bunch of these all over the place. So this is a paradigm shift in delta V missions. A lot of times we talk about things like the solar gravitational lens, or we talk about visiting Kuiper or Oort cloud objects. But this is a different dynamic in that it's a delta V problem, not a distance problem. Next slide. So with that, the technology I'm going to talk to you about isn't incredibly, novel, in that NASA looked at a lot of radioisotopes back in the 60s. They had polonium and cesium and strontium. Russians launched a lot of strontium. We've, over the last many, many years, have gotten used to plutonium-238. And a lot of the selection criteria for these is based on a generic mission architecture of, we're going somewhere far in the outer solar system and we need about 50 to 100 years of power. But that's not the case with these types of objects. If you are able to spot them and look at their trajectory, then even if they're leaving the solar system, or even if you catch them at a bad time, if you have you can complete a mission in something like 10 years, 15 years. And there's actually been a lot of work done. Project Lyra has done a ton of orbital mechanics looking at, hey, if we had, X kilometers per second at delta V at this date, how fast could we catch up to these objects? So the general consensus was for that project, looking mostly at chemical systems, was 35 kilometers per second at delta V leaving in 2027 could get you a flyby in something like 15 to 20 years. So 35 kilometers per second is a flyby, but I'm talking about something that, there are a lot of great sail concepts out there. I love the NIAC sail concepts, but something that we can do that's unique with radioisotopes is that we can slow down when we get there. We don't need solar energy. We can basically, leave Earth at a high, do a gravity slingshot around Jupiter, most likely, get into the plane of the object, intercept it, and actually slow down and check it out, and then come back to Earth. And that's the type of mission architecture that's enabled by really this idea that, hey, forget plutonium, save plutonium for Pluto, and let's look at shorter lived isotopes, and specifically cobalt-60. Next slide. So we actually have been working on a technology that is a generic isotope production technology at my company, USNC Tech. This is something that you start out, you manufacture it in a lab with the proper precursor. You encapsulate it before you irradiate it later, so you have this dual ceramic architecture. Then you put it in the neutron reactor, and those neutrons interact with the precursor material, the ooey gooey center, and they convert it into the radioisotope of choice. And some people say, oh, you aren't getting 100% conversion. Well, we don't need 100% conversion. With something like cobalt-60, the power density, because it has a short half-life, is about 17 grams per watt, ideally. And if we even got 4 grams, 17 watts per gram. And if we even got 4 watts per gram or 3 watts per gram, it's actually fairly revolutionary. So the goal is not to get 100% cobalt-60, it's to have an easy producible architecture that you can produce a lot of these for. And we're developing this mainly looking at another isotope called thulium-170, which is not useful for this mission, but it's useful for missions to the moon. Thulium-170 has a higher power density than, for example, plutonium-238, but it has a very short half-life, 129 days. So next slide. So this is kind of the near-term architecture, and we're actually looking at flying these demonstration units in the near future, and then watt scale units, and scaling that to kilowatts. There are some supply chain challenges with producing radioisotopes, but for reference, the medical industry produces about 100 kilowatts of cobalt-60 every year, and that's far below what you could do if you had a concerted effort. Actually, cobalt-60 is starting to fall out of favor in the medical industry in favor of a lot of proton treatment. So there's potential for us to continue looking at something like cobalt-60 or other isotopes or other production methods. Next slide. So let me put this in context. You're never going to use a radioisotope for a large human mission. It's a lot of radioisotope. But this is really enabling because you can cut it into smaller pieces and you can look at small sats, things metric ton and under, and enable them to achieve the specific mass levels that nuclear electric propulsion, traditional fission nuclear electric propulsion can achieve. But the problem with NEP is that you need a very large vehicle to even start, kind of megawatt scale vehicles to start looking attractive on the specific mass levels. Another benefit of this is that you don't get any neutrons. So it's very nice with things like thermionics, where the Russians and the Topaz system actually put up thermionic fission reactors, but they had problems with neutron swelling. But a lot of those materials don't have the same problems. Solid state material for power conversion has significantly less challenges with X-rays than they do with neutrons. So there's some interesting things when you compare these. Next slide. So this is the concept we came up with for the NIAC program, a roughly 100 kilowatt thermal cobalt-60 system. And there's a lot of assumptions built into here, but the basic idea is this is solid state power conversion. Didn't want to go too crazy. In NIAC, you asked for one miracle, not two. So the power conversion actually uses TRL5 JPL thermoelectrics that they've been working on. There's segmented high temperature thermoelectrics that could, if I took it at face value, can get you even 12, maybe even 14% efficiency. Another benefit of the cabs is that you can get to the high temperatures. There's no moderator. There's nothing that's temperature sensitive. It's a dumb hot rock, right? It's something that produces heat. And you can compare it with, you don't need a control system. You don't need control rods. You just need to pair it with perhaps a solid state power conversion system that is preferably X-ray tolerant because there are a lot of X-rays coming out of many of these. So this is the fundamental concept, and really the thing that has to be figured out is, in my opinion, the production of the radioisotope, and that's where a lot of the focus of the study was on. But we also looked at a lot at the power conversion architectures, trying to drive towards that 5 kilograms per kilowatt. Next slide. So another key innovation here is regulatory. That up until about 2 years ago, there was nothing that allowed commercial companies to put things into space that were nuclear, at least radioisotope or fission. But there was recently a memo released, and this memo directed the FAA to be the regulator. And there's at a tier 2 level, you end up with an INSERB somewhat similar to the old process. But the idea is that commercial companies can do this. And this is something that, nobody, when I submitted this to NIAC, the thing was, hey, this is, what we want you to prove that you're right on is the regulatory part. Are you going to be allowed to launch this? Not, it's not so much that there's some new physics here. It's that there are regulatory and some power conversion challenges that prevent this from, in many people's eyes, being a good technology, or not so much a good technology, but something that someone can actually use for a mission and not have to spend billions of dollars for launch approval. So, this is a very in-depth topic, but we are actually looking at launching tier 1 radioisotope systems with our Lunar systems. For this particular mission, it would be a tier 2, but a unique thing that you find with a lot of this is that the difference between plutonium and cobalt in terms of what falls under the lower category of radioisotope is that you can have about 16 kilowatts of cobalt-60 before you run into problems. Whereas plutonium-238, you have 90 watts of power before you run into a tier 2 system. So from a regulatory standpoint, a lot of these gamma emitters and beta emitters are much less penalized because generally it's an inhalation or a gets in the groundwater type of dose thing, whereas cobalt-60 is not nearly as bad as plutonium in those types of situations. So anyways, there's a lot I could go into here. I don't think a lot of the people in the audience there's a lot of nuances to this that I could talk about for hours. Next slide. So based on the knowledge that, hey, if you have, the limitation here is production of radioisotope in many ways. The cost to produce it, the reactors you need to put it in, it's a supply chain challenge. So what could you do with less radioisotope over kind of a 10-year mission? And the idea is that, okay, what's your payload mass? So on the y-axis here, we see various payload masses. On the x-axis, we see various ISPs. And, if you have, instead of 100 kilowatts, you go down to 10 for the same 20 kilogram payload, which we baselined, we're talking somewhere in the realm of still like 85 kilometers per second of delta V. And that's a lot. So, imagine 10 of these. Instead of just having one, you could have 10 of them. And another key thing about this is we have to wait for these interstellar objects to fall into our solar system. So what if 2 fall in at the same time? Or, the idea is that the more spacecraft that we can have on demand, perhaps the more effective the architecture, especially as we start getting some of these facilities such as, I believe, the LSSW. I'm forgetting what it stands for, but it's supposed to detect many of these objects, as many as perhaps 1 or 2 a year when that's running. And then even going down to 1 kilowatt of thermal power, that could enable a flyby of Oumuamua. In reality, if we can get, assuming a flyby is a little bit less payload mass, maybe 5 kilograms, you could still get 50 to 60 kilometers per second of delta V out of those types of systems. And that would be more than enough that if it launched within the 2020s, it could return flyby data for Oumuamua in about 10 to 15 years. So there's a lot of flexibility you can get on these extrasolar objects. And this technology is interesting. It's not a catch-all, it's not a cure-all, it's not something that we're going to necessarily use for the gravitational lens or going out to do anything interstellar, but it represents a step change in the kind of chemical and architectures that we see today towards 100 kilometers per second of delta V. Next slide. So with that, I'd love to talk more to people. The idea here is where this is a commercial product. The NIAC represents the kind of future potential, and the near term is kind of more of looking at RHUs that are commercial. And if anyone's interested in this type of thing, and for the interstellar crowds, there actually is one isotope here that we are looking at that has about 1,000-year half-life. It's not very power dense, but the idea might be you put it on your probe and it might give you a few watts of power when you're at Alpha Centauri or something like that. So if anyone's interested, I'd love to chat more.
All right. So we do have a question. Could you land on some of the near Earth objects and hitch a ride into space? It looked as if your intercept missions probably allowed for something of that nature, but could you expound upon that a little bit more?
Yeah, so the idea is that the CONOPS of the mission is that we have a telescope that detects a near Earth object. It might be inbound, it might be outbound, but the standard architecture is we launch, or maybe we have something waiting in a high orbit, maybe a Lagrange point, and it executes a plane change maneuver around Jupiter. So it flies out to Jupiter, does a plane change. There might be other planets, depends on the alignment of the planets and various things like that. But and then it flies out, and as it's flying out, it's accelerating halfway to the object, and then it's decelerating the other halfway to the object. It's very when you deal with these high, when you deal with delta V's that are well above escape velocity, it's kind of like kinematic equations. You accelerate halfway, you decelerate the other halfway, and you end up, basically rendezvousing with these objects. And while you're there, you could totally hang out and, if it has a strong enough gravitational field, orbit it and check it out. But the payload that we notionally put on it was a Hayabusa 2-like sample return mission, the one where you fly up close to the object, you shoot a bullet into it, and then you capture a few grams of sample. Now, would that work on an object that might be like solid nitrogen or something like that? I don't know. It's kind of like a notional. I don't know what a sample return type payload would look like, but if you carried a secondary payload, you could totally leave maybe a flyer or even a rover or something on the object as it travels out. The idea was that you bring back a sample from that object, and you would look at things like isotopic analysis and various things like that. And another possible conopsis is you're flying up to it, make sure it's not an alien object, because you're a very at least the front of the spacecraft is very radioactive. So if it stay away, try to communicate at a distance if it's an alien spacecraft.
I'd like to try to make sure that I understand this a little bit correctly. Would you be able to tune your specific impulse by selecting the different types of radioisotopes? And like for shorter, higher impulse missions, you would select a radioisotope with a short half-life and a pretty rapid decay?
Absolutely. Yeah, that's the idea behind it, is that all radioisotopes they're different, but they have about the same amount of energy in them. Their half-life determines how fast that energy is emitted. So if you pick a short half-life material, it's like a boost of energy in the beginning. A longer half-life of material, it's kind of spread out over a longer time. And I will say, once you get beyond maybe about 30 years, plutonium is looking pretty darn good. It's pretty hard to beat, but we do have a lot of good ones that are, think of maybe 30 years or less, that could potentially be very useful. There's the caveats of, hey, we're putting out a lot of X-rays. How do we deal with these X-rays? Distance, possible shielding, and things like that. But yeah, for the lunar missions, we're looking at the 129-day half-life thulium's technology is perfect, because a lot of those people, they want to survive a few lunar nights, but they don't want to support a mission for 10 years, type of thing.
Are you able to save a little bit of mass by switching instead from the heavy transuranics to something along the lines of a technetium?
Yeah, so there's only so many isotopes we can make in the process that I described. So there's, on the chart of nuclides, I think 1,700 nuclides or something like that. The ones we can make, there's generally about a dozen of them that we can make effectively with various half-lives. So technetium is one that is not something we can make with a fission reactor, but there are interesting accelerator and neutron-based fusion and other things where we could actually make more isotopes using a lot of these methods. But the fission reactor currently has the highest flux. So what I'll say is the transuranics, they're some of the best materials in terms of their power per unit mass. Their decay, they might have like a 5 MeV alpha or something like that, whereas cobalt-60 is about 2.6 MeV. So they're very similar in terms of energy density, but in terms of power density, because of the perfect half-life of cobalt, the power density of cobalt-60 is about 30 times that of plutonium-238.
Okay, that takes us to a minute.
I think we're actually on time. So is that it?
All right.
All right.
Thank you.
Chris, great job. Thank you.
Yeah, thank you.
All right. We are scheduled to end this plenary session at 4:40 p.m. It is 4:40 p.m. We're on time. I really want to thank the 14 speakers we had today from a couple of aspects. One is by keeping to the very compressed schedule, so that's tough to do. And so for all of you who are doing that today, I appreciate it. You've set a high bar for the folks tomorrow and on Monday. I also want to thank them, those of you who've been involved in technical conferences before. Will appreciate what I'm saying when I say that all of these slides arrived here Monday. Nobody walked in with a thumb drive saying, I did these on the airplane. I have a couple of changes. They didn't do that. They got them all here Monday. We preloaded them, and that made the Zoom call much more effective. We've had running between 30, 35, maybe 40 people on the Zoom call during the day. Glad they're part of it. If you're still listening to it, thanks for sticking with us. We are going to cut off the Zoom connection at the end of this. So here's what's happening next. We're going to let you get up, wander around. The posters are out there in the Ventana room. The posters are up. When the program committee went through the selection process to select the abstracts that turned into the discussions you're seeing on screen, we just had too many good ones. And there's only so many, you can only squeeze 8 pounds into a 5-pound sack. We already compressed the slots from 30 minutes to 20 minutes. And so what we did is we said, you know, the next batch, the ones that were just almost good enough, or in some cases a little late, but quite good, we converted those to poster presentations. So we've got over a dozen of those in the Ventana room. They're there now. You're welcome to wander around on your own and take a look at them. We are asking all of the authors of posters to be in the room at 6 o'clock at the Ventana room, because that way somebody, if they want to talk to you about their poster, or about your poster, they know they can find you there at 6 o'clock. So that's the plan for that. That will run until 7. We'll close the doors of Ventana room at 7. Everybody goes across the hall, actually right through that wall. And we will have the Eridani Award banquet. That'll run from 7 to 9. We'll have a small award ceremony. And then Homer Hickam, who was in the room earlier, I can't see with this light, but if Homer is here, raise your hand. He may be in the other room. Homer, author of Rocket Boys, which turned into October Sky, is going to be our dinner speaker, and he's awesome, so you don't want to miss that. That will run until close to 9 o'clock, and then we'll start the working tracks at 9. So the day's not nearly over, but the plenary sessions are over. We're going to kill the Zoom feed. Thanks for sticking around. We appreciate it. We'll see you in the Ventana room, then we'll see you at dinner. Thanks.